Good evening and welcome to Physic for Sleep. Tonight we embark on an intellectual journey exploring the breathtaking landscape of quantum physics, from its foundational principles to the intricate tapestry of quantum field theory. Before we gently immerse ourselves in the elegant strangeness of the quantum realm, I would like to know where you are at this moment. Perhaps you are gazing out a window, watching the gentle fall of rain against the glass, wrapped in a soft blanket. If these deep reflections help you relax and organize your thoughts before sleep, please support the channel with a like and subscribe so others can find their way here too. Now, just breathe. Allow your eyes to grow heavy, and let's begin. The universe, as we perceive it in our everyday lives, often appears as a continuous, unbroken canvas, a flowing tapestry where quantities like energy and motion seem to vary without limit. Yet, as the 19th century drew to a close and the 20th began, physicists encountered a series of perplexing phenomena that stubbornly defied these classical explanations, hinting at a deeper, more granular reality beneath the surface of appearances. It began, quite unexpectedly, with the seemingly innocuous problem of black body radiation, the characteristic spectrum of light emitted by any object solely due to its temperature. Imagine a piece of hot metal glowing red, then orange, then white as it gets hotter. Classical physics, with its elegant equations, predicted an unsettling anomaly, the ultraviolet catastrophe. This theory suggested that an ideal hot object should emit an infinite amount of energy at very short wavelengths, like ultraviolet light and beyond, which was demonstrably not observed in experiments. The universe simply did not behave that way, leaving a gaping wound in the heart of classical physics. It was Max Planck, in the year 1900, who introduced a revolutionary, almost desperate hypothesis to resolve this glaring paradox. He proposed, with a degree of reluctance at first, that energy is not emitted or absorbed continuously, like water flowing from a tap, but rather in discrete, indivisible packets, which he termed quanta. To grasp this, consider an analogy. Imagine trying to climb a perfectly smooth, continuous ramp. Classical physics suggested you could rest at any infinitesimal height. Planck, however, suggested that energy was more akin to a staircase, where you can only stand on specific, distinct steps, and cannot exist anywhere in between them. Each step represents a quantum of energy, and its size, its magnitude, is directly proportional to the frequency of the radiation, scaled by a truly fundamental constant, now universally known as Planck's constant, or simply h. This incredibly tiny, yet profoundly significant number represents the smallest possible unit of action in the universe, a kind of indivisible currency of reality at its most fundamental level. This was not merely a convenient mathematical trick to make the equations fit the experimental data. It was a radical shift in perspective, suggesting for the first time that the very fabric of energy itself possessed a fundamental granularity, a kind of atomic structure, much like matter. This audacious notion of energy existing in discrete packets found further, even more compelling, empirical support with Albert Einstein's brilliant explanation of the photoelectric effect in 1905. This phenomenon involves light shining on certain metals, causing them to eject electrons. Classical wave theory, which had successfully described many aspects of light, predicted that the energy of these ejected electrons should depend primarily on the intensity of the incident light, and that any frequency of light, given enough intensity and time, should eventually dislodge electrons. Yet, meticulous experiments consistently showed otherwise. Electrons were only ejected if the light's frequency was above a certain critical threshold, regardless of how intense or bright the light source was. Below that specific frequency, no electrons were emitted, no matter how long the light shone or how powerful its beam. Einstein, with characteristic insight, built upon Planck's pioneering idea and proposed that light itself consists of individual discrete packets of energy, which he initially called light quanta, and which we now famously refer to as photons. Each photon, he posited, carried a specific amount of energy directly proportional to its frequency. If a single photon did not possess enough energy, that is, if its frequency was too low, it simply could not knock an electron free from the metal, regardless of how many such low-energy photons struck the surface. Conversely, if a single photon had sufficient energy, it could instantly eject an electron, even if only a few such high-energy photons were striking the material. This groundbreaking insight not only explained the photoelectric effect perfectly, but also provided undeniable evidence that light, which had been understood purely as a wave phenomenon for centuries, also exhibited undeniable particle-like behavior. And here, dear listener, we encounter the first truly profound and perhaps the most counterintuitive mystery of the quantum world: wave-particle duality. Light, which we experience and model so successfully as waves. Think of the shimmering, continuous patterns on a pond's surface, or the elegant way colors separate and blend in a rainbow or a prism. Also manifests as distinct, localized particles, these discrete photons. It is not a choice between one or the other. It is both, simultaneously maintaining these seemingly contradictory natures. This duality is not merely an abstract philosophical concept. It is the fundamental bedrock of how light interacts with matter and energy at the quantum scale. The universe, in its intricate and subtle wisdom, seems to utilize both aspects depending on the specific circumstances, weaving an eternal and complex dance between continuous flow and discrete packets. It is a reminder that our macroscopic intuition, formed by observing large objects, often falls short when we delve into the infinitesimal. But the quantum revelations, as you might imagine, did not stop with light. The stage was set for an even more audacious leap. Louis de Broglie, a French physicist in 1924, extended this radical idea to matter itself. He hypothesized in his doctoral thesis that if light waves could behave like particles, then perhaps particles of matter, such as electrons, protons, and indeed all fundamental constituents of the universe, could also exhibit wave-like properties. This was an astonishing claim, for we typically observe electrons as distinct, localized particles within atoms, much like tiny planets orbiting a central sun, though that classical image is itself an oversimplification. Yet, de Broglie proposed that every particle has an associated wavelength, now known as the de Broglie wavelength, which is inversely proportional to its momentum. This means that the heavier an object and the faster it moves, the shorter its de Broglie wavelength becomes, rendering its wave nature utterly imperceptible in our everyday macroscopic world. This is precisely why we do not perceive ourselves, or a thrown baseball, or even a grain of sand, as waves. Our wavelengths are infinitesimally, immeasurably small, far beyond any detection. This theoretical leap, initially met with skepticism, was soon confirmed experimentally in 1927 by American physicists Clinton Davison and Lester Germer, and independently by George Paget Thomson in Scotland. They observed electrons diffracting, or spreading out in a wave-like pattern, when fired at a nickel crystal. Just as X-rays, a well-known form of electromagnetic wave, diffract when passing through a crystal lattice, creating distinct interference patterns, so too did these streams of electrons. This profound discovery cemented the idea that matter, at its most fundamental level, is also dualistic. An electron is not simply a tiny billiard ball with a definite position and trajectory. It is also, simultaneously, a spread-out wave of probability. And this wave doesn't just describe where the electron might be. In a profound sense, it describes the electron itself before it is definitively measured or forced into a particular state. This inherent wave-like nature of matter profoundly changes our most fundamental understanding of reality. It means that the basic building blocks of everything around us, and indeed within us, every atom, every molecule, every cell, are not solid, distinct points, but rather fuzzy, extended probability distributions. When you consider the solidity of the chair you might be resting in, or the very atoms that compose your hand, they are not fixed, definite entities in the classical sense. Instead, they are manifestations of these underlying wave functions poised between possibilities until an interaction, an observation, brings them into a concrete state. This is not a weakness or an incompleteness of our understanding, but rather a profound intrinsic feature of nature itself. The universe, at its core, is a dynamic realm of potential and probability, where the familiar solidity and definiteness of objects emerge from the collective behavior of countless unseen waves. It is a beautiful, if unsettling, realization that even our own existence is fundamentally tied to these quantum uncertainties. This initial foundational insight into quantization and wave-particle duality lays the essential groundwork for the deeper mysteries we are yet to explore, gently guiding us towards a reality far richer, more intricate, and more wonderfully strange than our everyday senses alone might ever suggest. As we gently drift deeper into the quantum realm, having encountered the strange duality of waves and particles, we find ourselves needing a new language, a new way to describe this profoundly different reality. The classical world, with its precise trajectories and predictable outcomes, simply cannot capture the inherent fuzziness and probabilities that govern the smallest constituents of existence. This is where the concept of the wave function emerges, a central pillar of quantum mechanics. Imagine, if you will, that every particle, be it an electron, a photon, or even a proton, is not merely a tiny hard sphere, but rather a spread-out cloud of potential existing across a region of space. The wave function, often denoted by the Greek letter psi or pex, is the mathematical entity that precisely describes this cloud, encoding all the information we can possibly know about a quantum system. It doesn't tell us exactly where a particle is, but rather where it is likely to be. This probabilistic interpretation, famously formulated by Max Born, suggests that the square of the magnitude of the wave function at any point in space gives us the probability of finding the particle at that specific location if we were to perform a measurement. It is not that the particle is at multiple places simultaneously, but rather that its existence is fundamentally undefined across a range of possibilities until an interaction forces it to manifest in a single, definite spot. Think of it less as a physical wave spreading through space and more as a wave of information, a potential landscape for the particle's presence. Before observation, the particle is, in a profound sense, smeared out across all its possible locations, a cloud of likelihoods. This shifts our understanding from a universe of definite things to one of probabilities and potentials, a subtle yet monumental change in perspective. And as we consider this, we might wonder, does our own presence, our own consciousness, play an active role in shaping the reality we perceive from this sea of possibilities? The evolution of this mysterious wave function is governed by another cornerstone of quantum theory, the Schrödinger equation. Developed by Erwin Schrödinger in 1926, this mathematical equation acts as the quantum world's equivalent of Newton's laws of motion. While Newton's laws predict the precise trajectory of a billiard ball, the Schrödinger equation predicts how the probability distribution of a quantum particle changes over time. It is a deterministic equation, meaning that if you know the initial wave function of a system, you can, in principle, calculate its wave function at any future moment with absolute certainty. However, the outcome of any specific measurement on that system remains inherently probabilistic. The equation doesn't tell us where an electron will land, but rather the probabilities of it landing in various places. This fundamental difference marks a profound departure from classical physics, where perfect knowledge of initial conditions would lead to perfect prediction of all future states. The Schrödinger equation also elegantly explains the existence of quantized energy levels within atoms. Just as Planck first proposed that energy comes in discrete packets, the solutions to the Schrödinger equation for particles confined within a potential well, like electrons bound to an atomic nucleus, reveal that they can only occupy specific, discrete energy states. They cannot possess any energy value in between these allowed levels. This is why atoms emit and absorb light only at very specific wavelengths, leading to their unique spectral fingerprints. Imagine a musical instrument that can only play certain notes, never sliding between them. Atomic electrons are much the same, jumping between these distinct energy steps as they absorb or emit photons. This quantization of energy is a direct observable consequence of the wave-like nature of matter confined within a small space, profoundly shaping the stability and chemical properties of all elements, and indeed, the very structure of the universe around us. This leads us directly to the perplexing concept of superposition. If a quantum system can be described by a wave function that encompasses multiple possibilities, then, before measurement, the system exists in a superposition of all those possible states simultaneously. For instance, an electron might exist in a superposition of spin up and spin down at the same time, or be in a superposition of being in two different locations simultaneously. This is not a matter of it rapidly switching between states or of our ignorance about its true state. Rather, it is genuinely existing in all these states at once, a blurred reality of coexisting possibilities. The famous thought experiment of Schrödinger's cat, locked in a box with a quantum trigger that might or might not release a deadly poison, vividly illustrates the apparent absurdity when we try to scale this quantum behavior to the macroscopic world. According to quantum mechanics, until the box is opened, the cat is in a superposition of being both alive and dead. Of course, in practice, a cat is a macroscopic system constantly interacting with its environment, which acts as a continuous measurement, rapidly collapsing any such superposition. But for isolated microscopic particles, this simultaneous existence of multiple states is a fundamental truth. The moment we interact with a quantum system to determine its state, the act of measurement, is when this superposition vanishes. The wave function, which described all the potential states, collapses into a single, definite outcome. The electron that was suddenly registers as either spin up or spin down. The particle that was spread out across a region is now found at a single point. This process of wave function collapse remains one of the most enigmatic and debated aspects of quantum mechanics. What constitutes a measurement? Does it require a conscious observer, or is any interaction with the environment sufficient? Different interpretations of quantum mechanics offer varying perspectives, from the many worlds interpretation, which suggests all possibilities are realized in parallel universes, to objective collapse theories, which propose a physical mechanism for collapse independent of consciousness. Regardless of the interpretation, the empirical fact remains. Our observation profoundly affects the reality of the quantum system. It is as if the universe holds its breath, its options open, until we ask a specific question, at which point it commits to a single answer, transforming potentiality into actuality. And finally, we arrive at one of the most iconic and profound statements of quantum reality, Werner Heisenberg's uncertainty principle, articulated in 1927. This principle states that there are certain pairs of physical properties called conjugate variables that cannot both be known with arbitrary precision simultaneously. The most famous example is position and momentum. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This is not a limitation of our measuring instruments, nor a result of clumsy observation disturbing the system. It is a fundamental, inherent property of the universe itself, woven into the very fabric of quantum mechanics. Imagine trying to precisely measure the position of a wave on water. If you try to pinpoint its location, you lose information about its wavelength and direction of motion. Conversely, if you measure its wavelength very precisely, you can no longer say exactly where the wave is. This applies to other pairs as well, such as energy and time. The more accurately you measure the energy of a system, the less precisely you can determine the time it possessed that energy, and vice versa. This means that at the smallest scales, reality is fundamentally fuzzy. not just due to limitations in our technology, but because the very concepts of a precise position and a precise momentum for a particle simultaneously cease to have meaning. It introduces an irreducible element of randomness and unpredictability into the universe, a profound departure from the deterministic clockwork universe of classical physics. This inherent quantum uncertainty underscores that the universe is not a perfectly defined machine, but rather a dynamic, probabilistic dance of possibilities, where even our most fundamental knowledge is constrained by the very nature of reality. And in this dance, we too are participants, inextricably linked to the grand, unfolding mystery. Having journeyed through the foundational principles of quantization, wave-particle duality, and the profound implications of the uncertainty principle, we now approach an even more exquisite and perplexing phenomenon: quantum entanglement. If the idea of a particle existing in multiple states at once seems strange, then entanglement takes us to a deeper, more interconnected level of reality, one where particles are no longer independent entities, but rather intimately linked, their fates intertwined in a way that defies our classical intuition. Imagine two particles, perhaps two electrons, that are created or interact in a special way. Once entangled, they remain connected, regardless of the vast distances that may separate them, whether they are across a laboratory bench or across the entire cosmos. If you measure a property of one entangled particle, such as its spin, the corresponding property of the other particle is instantaneously determined, no matter how far apart they are. This seemingly instantaneous correlation, as if information is traveling faster than the speed of light, famously troubled Albert Einstein, who derisively called it spooky action at a distance. He believed it implied an incompleteness in quantum mechanics, suggesting there must be hidden variables determining the outcomes from the start, rather than genuine randomness. However, decades of meticulous experiments, notably those by John Bell and later Alan Aspect, John Clauser, and Anton Zeilinger, have consistently demonstrated that entanglement is a very real, fundamental aspect of nature, and that no such hidden variables can explain these correlations. The particles do not know in advance what state they will be in. Rather, their states are indeterminate until one is measured, and at that very moment, the other instantly assumes its correlated state. It is not that information is transmitted, but that the single, shared quantum state of the entangled pair collapses simultaneously, revealing its definite properties. This profound interconnectedness suggests that at the quantum level, the universe is not merely a collection of isolated parts, but a deeply unified whole. To further appreciate entanglement, we must briefly consider another fundamental quantum property: spin. Unlike the classical notion of a spinning top, the spin of a quantum particle like an electron is an intrinsic property, an angular momentum that does not arise from actual physical rotation. It is more akin to an innate magnetic moment, a fundamental characteristic that helps define the particle itself. Electrons, for instance, are fermions, meaning they have a half-integer spin, typically referred to as spin-up or spin-down, along a given axis. These are not merely labels, they are distinct quantum states. When two electrons become entangled, their spins can be perfectly correlated or anti-correlated. If one is measured to be spin-up, the other must be spin-down, or vice versa, even if they were light years apart and neither had a definite spin state before the measurement. This intrinsic spin is crucial for understanding how atoms are built, how materials behave magnetically, and it provides a powerful example of a purely quantum mechanical property with no direct classical analog. The mathematical framework that underpins these profound concepts is often described using the language of linear algebra, particularly the idea of Hilbert spaces and operators. While we need not delve into the intricate equations, it is helpful to understand the conceptual landscape. A quantum state, like the wave function we discussed, can be represented as a vector in an abstract mathematical space known as a Hilbert space. This space allows for the representation of superpositions, where a single vector can be a combination of multiple basis states. For example, a vector representing an electron that is simultaneously spin up and spin down. Physical observables, such as position, momentum, energy, or spin, are represented by mathematical entities called operators. When we perform a measurement, we are essentially applying one of these operators to the quantum state, and the outcome of that measurement corresponds to one of the eigenvalues of the operator, forcing the state to collapse into a corresponding eigenstate. This abstract mathematical language provides a precise and consistent way to describe the probabilistic nature of quantum reality, allowing physicists to make accurate predictions about experimental outcomes, even if the underlying reality remains deeply counterintuitive. The interpretation of what these mathematical descriptions truly mean remains one of the most vibrant and debated areas in physics. The measurement problem, the question of how and why a quantum superposition collapses into a single definite state upon observation, has led to various schools of thought. The Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg, is perhaps the most widely accepted. It posits that the wave function is not a physical entity, but a mathematical tool for calculating probabilities, and that observation itself, involving an interaction with a macroscopic measuring device, is what forces a quantum system to choose a definite state. Before measurement, there is no inherent reality to the specific properties. They exist only as probabilities. Another influential perspective is the many worlds interpretation proposed by Hugh Everett in 1957. This interpretation suggests that when a measurement occurs, the universe doesn't choose one outcome. Instead, it splits into multiple parallel universes, with each possible outcome being realized in a different branch. In this view, the cat in Schrödinger's thought experiment is both alive and dead, but in separate, non-interacting realities. While no interpretation has achieved universal consensus, these profound discussions remind us that quantum mechanics challenges not just our understanding of particles, but our very definition of reality itself, inviting us to contemplate the vastness of possibilities. Beyond these fundamental concepts, quantum mechanics also predicts phenomena that are utterly impossible in the classical world, yet have been repeatedly observed. One such marvel is quantum tunneling. Imagine a ball rolling towards a hill. Classically, if the ball does not have enough energy to roll over the top of the hill, it will simply roll back down. It cannot appear on the other side. However, in the quantum realm, a particle can, with a certain probability, effectively tunnel through an energy barrier, even if it does not possess sufficient energy to surmount it. This is a direct consequence of the particle's wave-like nature. Its wave function does not abruptly drop to zero at the barrier, but rather decays exponentially within it, meaning there is a non-zero probability of finding the particle on the other side. This isn't magic, but a fundamental aspect of quantum probability. Quantum tunneling plays a crucial role in many natural processes, from the nuclear fusion that powers our sun, where protons tunnel through their mutual electrostatic repulsion to combine, to radioactive decay, where alpha particles tunnel out of atomic nuclei. It is also the operational principle behind technologies like the scanning tunneling microscope, which allows us to image individual atoms by exploiting the tunneling current of electrons. These tangible manifestations of quantum strangeness continually reveal a universe far more subtle and interconnected than our everyday experiences suggest, inviting us to expand our sense of what is truly possible. And in this expansion, we find a profound calm, knowing that even the most improbable events are part of the universe's grand design. As our journey through the quantum world deepens, we find that the initial framework of quantum mechanics, while revolutionary, had its own limitations. It excelled at describing individual particles moving at relatively low speeds, confined within atoms, or navigating simple potentials. Yet, the universe is also a realm of immense energies, where particles hurtle close to the speed of light, and where new particles are constantly being created and annihilated. To truly grasp these dynamic processes, physicists realized they needed to weave together the insights of quantum mechanics with Albert Einstein's theory of special relativity, leading to the development of relativistic quantum mechanics. This fusion was a monumental step, as special relativity fundamentally alters our understanding of space and time, and thus how particles behave when their speeds approach that ultimate cosmic limit. One of the most profound early successes of this relativistic quantum mechanics came in 1928 with the brilliant work of Paul Dirac. He formulated an equation that elegantly combined the principles of quantum mechanics with special relativity, aiming to describe the behavior of electrons. What emerged from this mathematical tapestry was astonishing. Not only did the Dirac equation accurately predict the electron's spin, a property that had previously been added somewhat ad hoc to quantum theory, but it also predicted the existence of an entirely new particle, one with the same mass as the electron, but an opposite electric charge. This was the anti-electron, or positron, the first predicted instance of antimatter. Imagine, if you will, the universe not just containing matter, but a mirror image counterpart, a shadow twin for every particle. Dirac's prediction was initially met with a mixture of awe and skepticism, as it seemed almost too elegant to be true. Yet, just 4 years later, in 1932, Carl Anderson experimentally confirmed the existence of the positron, observing it in cosmic ray interactions. This discovery opened up an entirely new dimension of reality, showing that particles can have corresponding antiparticles and that matter and antimatter can be created from pure energy and can annihilate each other, transforming back into energy. This fundamental symmetry between matter and antimatter is a cornerstone of our modern understanding of the cosmos, hinting at a deep balance in nature. This brings us to the Standard Model of particle physics, a comprehensive theory that describes the fundamental particles and forces that govern the universe, excluding gravity. Think of it as the ultimate periodic table. But for the most basic constituents of reality, the Standard Model classifies all known fundamental particles into two main categories: fermions, which are the matter particles, and bosons, which are the force-carrying particles. Among the fermions, we find quarks, which combine to form protons and neutrons, the building blocks of atomic nuclei, and leptons, which include the familiar electron, as well as its heavier cousins, the muon and the tau, along with their elusive neutrino partners. These matter particles possess intrinsic properties like mass, charge, and the aforementioned spin. Then there are the bosons, the messengers of interaction, the photon, mediating the electromagnetic force, the W and Z bosons, responsible for the weak nuclear force involved in radioactive decay, and the gluon, carrying the strong nuclear force, binding quarks within protons and neutrons. And, of course, the Higgs boson, a particle associated with the Higgs field, which permeates all of space and is thought to give fundamental particles their mass. This model, developed over decades of theoretical insight and experimental verification at particle accelerators like the Large Hadron Collider, offers a remarkably successful description of the subatomic world, a profound testament to humanity's quest to understand the very essence of existence. However, even the Standard Model, with its impressive predictive power, needed a deeper conceptual foundation. This is where quantum field theory, or QFT, enters the picture, offering a more complete and elegant framework for understanding particles and their interactions. In QFT, the fundamental entities are not discrete particles, but continuous fields that permeate all of space-time. Imagine the entire universe filled with an invisible, vibrating ocean of these fields. Each type of fundamental particle in the Standard Model, the electron, the photon, the quark, is understood not as a distinct immutable object, but as a tiny ripple, a localized excitation, or a quantum of its corresponding field. For example, the electron field exists everywhere, and an electron particle is simply a vibrational mode, an excited state of this universal field. Similarly, The photon is an excitation of the electromagnetic field. This reinterpretation is profoundly elegant because it naturally accounts for wave-particle duality. The field itself is continuous and wave-like, while its excitations appear as discrete particles. Particle creation and annihilation, which are commonplace in high-energy physics, are then seamlessly described as the excitation or de-excitation of these underlying fields. This perspective also illuminates one of the most astonishing ideas in modern physics: that empty space is not truly empty. Even in the deepest vacuum, these quantum fields are constantly fluctuating, bubbling with activity. These are known as vacuum fluctuations, giving rise to virtual particles that pop into existence and almost instantaneously disappear, too fleeting to be directly observed, yet their effects are very real and measurable. The Casimir effect, for instance, which we touched upon earlier, where two uncharged metal plates placed incredibly close together in a vacuum experience an attractive force, is a direct consequence of these vacuum fluctuations. The fluctuations outside the plates have a wider range of possible wavelengths than those confined between them, leading to an imbalance of radiation pressure that pushes the plates together. These omnipresent quantum fluctuations are not merely theoretical curiosities. They are a fundamental aspect of reality, suggesting that even nothingness is teeming with potential energy, a restless sea from which all matter and energy ultimately arise. It reminds us that even when we feel alone, surrounded by silence, the universe itself is a vibrant, dynamic tapestry of unseen activity. To visualize the intricate dance of these interacting fields and their excitations, physicists employ a powerful conceptual tool called Feynman diagrams, introduced by Richard Feynman. These are simple, yet profoundly informative, pictorial representations of particle interactions. Imagine lines representing particles moving through space-time, converging at points called vertices, where interactions occur, mediated by force-carrying particles. For example, two electrons repelling each other would be depicted as two electron lines exchanging a photon. While seemingly straightforward, each line and vertex in a Feynman diagram corresponds to a complex mathematical term in the underlying QFT equations. These diagrams provide an intuitive way to categorize and calculate the probabilities of various quantum events, from particle scattering to the decay of unstable particles. They are a beautiful testament to the power of visualization in physics, transforming abstract mathematical processes into understandable, almost poetic, narratives of interaction within the quantum fields. However, the precision of QFT, especially when calculating interactions involving virtual particles, initially led to a daunting problem: the appearance of infinite values in the equations, suggesting a breakdown of the theory. This was a crisis, as physical quantities must always be finite. The ingenious solution came in the form of renormalization, a sophisticated mathematical procedure developed by physicists like Julian Schwinger, Richard Feynman, and Shinichiro Tominaga. Conceptually, renormalization involves acknowledging that the bare, theoretical values of a particle's properties, such as its mass or charge, are not what we actually measure in experiments. These bare values are effectively dressed by their continuous interactions with the surrounding sea of virtual particles, leading to observed finite values. By carefully accounting for these infinite self-interactions and absorbing them into a redefinition of the physical parameters we measure, physicists found a way to make QFT's predictions finite and incredibly accurate. This technical triumph transformed QFT from a problematic theory into one of the most successful and precisely verified theories in all of science, underpinning our understanding of the fundamental forces and particles. It is a subtle art, this renormalization, reminding us that even in the most abstract corners of physics, the quest for elegance and consistency ultimately reveals a deeper truth about the universe's inherent order. The triumph of renormalization in quantum field theory, as we explored, allowed physicists to tame the mathematical infinities that initially plagued their calculations, transforming what seemed like a broken theory into one of unprecedented predictive power. This rigorous mathematical framework, where particles are understood as excitations of underlying quantum fields, provided the bedrock for our most successful description of the subatomic world. It is within this profound paradigm that we can now delve into one of the most remarkable discoveries of modern physics: the Higgs mechanism, a process that explains how fundamental particles acquire their mass. For a long time, the origin of mass was a mystery. Why do some particles, like electrons and quarks, possess mass, while others, like photons, are massless? In the 1960s, a brilliant theoretical proposal emerged from the work of several physicists, including Peter Higgs, François Englert, and Robert Brout. They postulated the existence of a pervasive invisible field, now known as the Higgs field, that permeates all of space. Imagine this field not as a collection of particles, but as a kind of cosmic molasses, a universal medium that interacts with other fundamental particles. Particles that interact strongly with this field experience a resistance, a drag, which we perceive as their mass. The more a particle interacts with the Higgs field, the more massive it becomes. Conversely, particles like the photon, which do not interact with the Higgs field, remain massless, able to travel at the speed of light. The Higgs field itself has an associated particle, the Higgs boson, which is a quantum excitation of this field, much like a ripple on the surface of water. The experimental discovery of the Higgs boson in 2012 at the Large Hadron Collider in CERN was a monumental achievement, confirming a central prediction of the Standard Model and validating the Higgs mechanism. It provided a tangible piece of evidence for this omnipresent field, revealing that mass is not an inherent, immutable property of particles, but rather an emergent quality arising from their interaction with the fabric of space-time itself. This understanding profoundly reshapes our view of reality. Even the seemingly solid and substantial nature of matter around us and within us is ultimately a manifestation of these subtle, unseen interactions with a fundamental field. It is a quiet confirmation that the universe is far more interconnected and dynamic than our everyday perceptions suggest. Moving deeper into the architecture of QFT, we encounter the elegant concept of symmetries and their profound connection to conservation laws. In physics, a symmetry describes a property of a system that remains unchanged under certain transformations. For example, if the laws of physics are the same today as they were yesterday, that implies a symmetry under time translation, and Noether's theorem, a cornerstone of theoretical physics, tells us that this symmetry leads directly to the conservation of energy. Similarly, regardless of where an experiment is performed, this spatial translation symmetry leads to the conservation of momentum. In quantum field theory, Chateau, these symmetries become even more intricate and powerful, often taking the form of gauge symmetries. These are local symmetries, meaning the laws remain unchanged even if we perform a transformation that varies from point to point in space-time. The requirement for these local gauge symmetries within QFT is what dictates the existence of the force-carrying particles, the bosons, and defines their interactions with matter particles. It is a stunning realization. The very forces that govern the universe, electromagnetism, the weak nuclear force, and the strong nuclear force, do not arise arbitrarily, but are a necessary consequence of imposing these deep abstract symmetries on the quantum fields. The mathematical elegance of gauge theories compels the existence of photons, W and Z bosons, and gluons, explaining how they mediate interactions. It's as if the universe is built upon a foundation of exquisite mathematical harmony, where fundamental principles of balance and invariance give rise to the rich tapestry of interactions we observe. This underlying order provides a sense of profound calm, suggesting a universe that is not chaotic, but guided by deep, beautiful principles. Let us now turn our attention to two specific and remarkably successful quantum field theories that form the backbone of the Standard Model. quantum electrodynamics, or QED, and quantum chromodynamics, or QCD. QED is the quantum field theory of the electromagnetic force, describing how light and matter interact. It depicts electrons and photons as excitations of their respective fields and explains all electromagnetic phenomena, from the behavior of atoms to the operation of lasers. QED is often hailed as the most precisely tested theory in all of physics. Its predictions, such as the anomalous magnetic dipole moment of the electron, match experimental measurements to an astonishing 10 decimal places. This incredible accuracy is a testament to the power of QFT and renormalization. It means that our understanding of light and electricity at the most fundamental level is extraordinarily robust, allowing us to predict the subtle dance of particles with unparalleled confidence. Complementing QED, we have quantum chromodynamics, or QCD, which is the quantum field theory of the strong nuclear force. This force is responsible for binding quarks together to form protons and neutrons, and for holding atomic nuclei together. Quarks, unlike electrons, carry a property called color charge, not a literal color, but an analogous quantum property that comes in 3 types: red, green, and blue. The strong force is mediated by particles called gluons, which themselves carry color charge, making their interactions much more complex than those of photons. A peculiar feature of QCD is color confinement, which states that quarks and gluons are never observed in isolation. They are always confined within composite particles like protons and neutrons. The force between quarks actually increases with distance, making it impossible to pull them apart. Imagine trying to stretch a rubber band that gets stronger the more you pull. Eventually, it would snap, creating new particles rather than allowing the original ones to separate. This confinement ensures the stability of matter, preventing quarks from existing freely and thus contributing to the structured universe we inhabit. As we conclude this exploration, it is important to acknowledge that the Standard Model, despite its incredible success, is not the final word. It does not include gravity, the fourth fundamental force, and thus cannot fully describe phenomena like black holes or the Big Bang. The quest to unify gravity with quantum mechanics, to develop a theory of quantum gravity, remains one of the greatest challenges in theoretical physics, leading to fascinating, albeit speculative, approaches such as string theory and loop quantum gravity. These theories attempt to describe space-time itself as quantized, a fabric woven from tiny fundamental units, hinting at a universe even more profound and interconnected than we currently imagine. The journey into quantum physics is one of continuous discovery, revealing layers of reality that challenge our deepest intuitions. It is a reminder that the universe, in its quiet complexity, holds endless wonders, inviting us to contemplate our place within its grand, evolving story. A story that is still being written, piece by quantum piece. And in this contemplation, we may find a tranquil sense of belonging within the vast, mysterious cosmos. Having thoroughly explored the intricate dance of quantum fields, the Higgs mechanism, and the foundational pillars of the Standard Model, we now arrive at the grandest challenge in modern theoretical physics, the elusive quest to unify gravity with quantum mechanics. The Standard Model, as remarkably successful as it is in describing the electromagnetic, weak, and strong forces, fundamentally omits gravity, the force that governs the large-scale structure of our universe, from the apple falling from a tree to the majestic spiral of galaxies. Albert Einstein's general theory of relativity, our most accurate description of gravity, portrays it not as a force in the traditional sense, but as the curvature of space-time itself, a smooth and continuous fabric. Yet, the quantum world, as we have seen, is characterized by discreteness, probabilities, and the inherent fuzziness of reality at its smallest scales. These two profoundly successful theories, general relativity and quantum mechanics, clash dramatically when we attempt to describe phenomena where both are critically important, such as the heart of a black hole or the very first moments of the Big Bang. At these extreme scales, where matter is compressed to unimaginable densities and space-time itself is thought to be wildly fluctuating, the smooth classical picture of gravity breaks down. Quantum mechanics insists that all forces must be mediated by particles, or quanta. For gravity, this hypothetical particle is called the graviton. However, efforts to construct a quantum field theory of gravity, similar to QED or QCD, have repeatedly run into insurmountable problems, typically yielding non-renormalizable infinities that cannot be tamed. It is as if the very mathematical language we use to describe the quantum world becomes inadequate when confronted with the fabric of space-time itself. This profound incompatibility has led physicists to search for entirely new theoretical frameworks that can reconcile these two pillars of modern physics, seeking a single, coherent description of reality that spans from the infinitesimal to the cosmic. The pursuit of quantum gravity represents a journey into the deepest mysteries of existence, inviting us to imagine a universe where space and time might not be what they seem. One of the most prominent and ambitious candidates for a theory of quantum gravity is string theory. This radical paradigm shifts our fundamental understanding of particles. Instead of point-like particles, string theory proposes that the universe's most elementary constituents are tiny, one-dimensional vibrating strings, unimaginably small, far beyond anything our current instruments could ever hope to resolve. Imagine these strings as minuscule cosmic rubber bands. Just as different vibrational modes of a violin string produce different musical notes, different vibrational patterns of these fundamental strings are thought to give rise to different types of particles. One mode of vibration might correspond to an electron, another to a quark, and crucially, one specific vibrational mode would correspond to the graviton, the elusive quantum of gravity. This elegant framework intrinsically includes gravity, weaving it seamlessly into the quantum tapestry alongside the other fundamental forces. A key, and perhaps startling feature of string theory, is its requirement for extra spatial dimensions beyond the three we perceive: length, width, and height, and the one dimension of time. These additional dimensions, typically 6 or 7 of them, are not macroscopically observable because they are thought to be compactified or curled up into incredibly tiny, intricate shapes, far too small for us to detect directly. Imagine a garden hose from afar. It appears as a one-dimensional line, but up close you see its circular, curled-up second dimension. Similarly, these extra dimensions are theorized to exist at every point in our familiar three-dimensional space, shaping the way particles interact and determining the fundamental constants of nature. The precise geometry of these curled-up dimensions could, in principle, explain the specific properties of all known particles and forces, offering a truly unified theory of everything. While still a theoretical endeavor, string theory offers a beautiful and consistent mathematical framework for unifying quantum mechanics and gravity, painting a picture of a universe composed of vibrating harmonies in a hidden, multi-dimensional space. Another compelling approach to quantum gravity is loop quantum gravity, or LQG, which takes a very different path from string theory. Instead of quantizing particles, LQG attempts to quantize space-time itself. It suggests that space, rather than being a smooth, continuous background, is fundamentally granular, composed of discrete, indivisible loops or atoms of space at the incredibly tiny Planck scale. Imagine a fabric woven from countless tiny threads, where the threads themselves are loops. As these loops interweave, they create a network, a spin network, which represents the quantum geometry of space. This theory predicts that even area and volume are quantized, meaning they can only take on discrete, minimum values. Time, too, is thought to be an emergent property in this framework, not a fundamental one. Loop quantum gravity offers a profound vision of a universe where space and time emerge from a more fundamental, discrete quantum structure. It is a non-perturbative approach, meaning it does not rely on approximations, and it has provided insights into the nature of space-time singularities, suggesting that the Big Bang might not have been a point of infinite density, but rather a big bounce from a previous contracting universe. While still under development and facing its own set of challenges, LQG provides a distinct and equally profound pathway to reconcile the quantum and gravitational realms, suggesting that the very container of our existence is itself a quantum phenomenon. Both string theory and loop quantum gravity, despite their differences, encourage us to stretch our imaginations, to consider the possibility that reality at its deepest level is far more intricate and wondrous than we could have ever conceived. Beyond the quest for quantum gravity, the principles of quantum mechanics are also finding astonishing applications in the burgeoning field of quantum information science, particularly in quantum computing. Classical computers store information in bits, which can be either a 0 or a 1. Quantum computers, however, utilize qubits, which can exist in a superposition of both 0 and 1 simultaneously. Moreover, multiple qubits can be entangled, allowing for incredibly complex correlations. These two quantum phenomena, superposition and entanglement, allow quantum computers to perform certain calculations at speeds and efficiencies far beyond the capabilities of even the most powerful classical supercomputers. Imagine a computation where every possible path is explored simultaneously rather than one by one. This is the essence of quantum parallelism. While still in its early stages of development, quantum computing holds immense promise for revolutionizing fields such as material science, drug discovery, and cryptography. It could enable the design of new materials with unprecedented properties, simulate complex molecular interactions to develop novel medicines, and break currently uncrackable encryption codes, while also creating new, quantum-secure encryption methods. The development of stable and scalable quantum computers is a formidable engineering challenge, requiring incredibly precise control over delicate quantum systems. Yet, the potential rewards are so vast that researchers worldwide are diligently pursuing this technological frontier. This practical application of quantum principles reminds us that the universe's most abstract truths often harbor the seeds of profound practical innovation, reshaping our future in ways we are only just beginning to comprehend. And as we consider the profound implications of these technologies, we might find a quiet sense of awe at the intricate connection between the smallest building blocks of reality and the vast potential of human ingenuity. Having navigated the profound intricacies of quantum fields, the mass-giving Higgs mechanism, and the Standard Model's elegant description of fundamental particles and forces, we now turn our attention to one of the most crucial conceptual bridges in all of quantum physics, the phenomenon of decoherence. We have seen how the quantum realm is characterized by superpositions, where particles can exist in multiple states simultaneously, and entanglement, where particles share an intimate, instantaneous connection, regardless of distance. Yet, our everyday macroscopic world appears stubbornly classical, filled with definite objects, clear outcomes, and independent entities. The question then arises, how does the blurry probabilistic quantum world give rise to the sharp, deterministic reality we experience? Decoherence offers a powerful and widely accepted explanation for this transition. Decoherence describes the process by which a quantum system loses its characteristic quantum properties, such as superposition and entanglement, due to its interaction with the surrounding environment. Imagine a perfectly isolated quantum particle existing in a superposition, like a ripple on a pristine, still pond. If that pond were truly isolated, the ripple would persist. However, in reality, no system is ever truly isolated. The quantum particle is constantly bumped into by countless other particles, photons, air molecules, thermal radiation, from its environment. Each tiny interaction, each bump, acts as an uncontrolled measurement, subtly probing the quantum system and causing its superposed states to become entangled with the vast number of environmental degrees of freedom. To grasp this, consider a quantum particle in a superposition of two locations. When it interacts with even a single photon from the environment, that photon effectively measures its position. If the photon then flies off into the vastness of space, carrying information about the particle's location, that information becomes irrevocably scattered and inaccessible. The quantum particle's original superposition is effectively erased from its local context as its quantum coherence spreads out into the environment. It's not that the superposition truly vanishes, but rather that it becomes so widely distributed and intertwined with the environment that it becomes practically impossible to reverse or observe. The particle no longer behaves as if it is in two places at once. It now appears to be in one definite location, and its wave function has effectively collapsed for all practical purposes. This is not an active, conscious observation, but a continuous, passive interaction with the thermal noise and quantum fields that permeate everything. This continuous interaction with the environment is incredibly rapid for macroscopic objects. A speck of dust, for instance, interacts with billions of air molecules and countless photons every fraction of a second. This constant barrage of measurements instantly destroys any macroscopic superposition or entanglement that might attempt to form. This is why Schrödinger's cat in its box is never truly for any observable duration. The cat, being a large, complex system, is continuously interacting with its internal and external environment, its own atoms, the air in the box, thermal radiation, causing its quantum state to decohere almost instantaneously. The environment acts as an unceasing observer, constantly forcing macroscopic systems into definite classical states. Decoherence thus provides a robust mechanism for the emergence of classical reality from the underlying quantum substrate, explaining why we don't observe everyday objects exhibiting the bizarre phenomena of the quantum realm. It is a testament to the seamless continuity of the universe, where even distinct realms are intricately connected. The profound implications of decoherence extend directly to the measurement problem, which we touched upon earlier. While decoherence doesn't resolve all philosophical debates surrounding measurement, it offers a crucial physical process that explains why macroscopic measurement devices always yield definite outcomes. It shifts the focus from the special role of a conscious observer to the unavoidable interaction between a quantum system and its much larger classical-like environment. In this view, the collapse of the wave function is not an arbitrary or mysterious event, but a natural, unavoidable consequence of information leaking out into the environment. The distinction between the quantum system and the classical measuring apparatus becomes less of a sharp divide and more of a gradual transition, mediated by the immense complexity of interaction. This perspective allows us to understand the apparent paradoxes of quantum mechanics not as fundamental flaws in the theory, but as features that simply do not manifest in systems that are in constant communication with their surroundings. Furthermore, decoherence is a critical challenge, and indeed a central obstacle in the development of quantum technologies like quantum computing. For a quantum computer to function, its qubits, the quantum bits of information, must maintain their delicate superpositions and entanglements for long enough to perform calculations. However, any unwanted interaction with the environment, even the tiniest stray photon or vibration, can cause these qubits to decohere, losing their quantum coherence and essentially reverting to classical bits. This makes building robust quantum computers an immense engineering feat, requiring extreme isolation, cryogenic temperatures, and sophisticated error correction techniques to protect the fragile quantum states from environmental noise. The battle against decoherence is at the forefront of quantum technology research, a meticulous dance between harnessing quantum power and shielding it from the ever-present classical world. Ultimately, decoherence teaches us that the universe is not neatly divided into a quantum world and a classical world, but rather that the classical world is an emergent property of the quantum world, appearing when quantum systems interact sufficiently with their environment. It is a process of information spreading, of possibilities narrowing, as the delicate quantum states become inextricably linked with the vastness of the cosmos. This continuous filtering of quantum possibilities into classical certainties unfolds constantly, moment by moment, around us and even within us. And as we consider this elegant transition, we might find a quiet reassurance that the solidity and predictability of our familiar world are not illusions, but rather the grand, stable patterns arising from the deeper, restless dance of quantum reality. May this understanding of the universe's inherent transitions bring you a sense of calm and clarity as you drift into tranquil sleep. Our journey through the quantum landscape has revealed a universe far more subtle and probabilistic than our classical intuition suggests. We've seen how particles are excitations of fields, how mass emerges from the Higgs mechanism, and how decoherence bridges the gap to our classical experience. Yet, even with these profound insights, the quantum realm continues to hold secrets that touch upon the very nature of existence, extending far beyond the subatomic particles to influence the grand cosmic stage. Let us now reflect on the quantum vacuum, a concept we briefly touched upon, and its astonishing role in shaping the universe itself. The quantum vacuum, far from being an inert void, is a seething ocean of ceaseless activity, a dynamic arena where energy and matter constantly borrow and return from existence. Even in the deepest reaches of space, seemingly empty, quantum fields are perpetually fluctuating, giving rise to virtual particles that spontaneously pop into existence, forming pairs of particles and antiparticles, only to annihilate each other in an incredibly short span of time. These ephemeral dance partners are a direct consequence of Heisenberg's uncertainty principle, allowing energy to be borrowed from the vacuum for durations so minuscule they remain just beyond direct observation. This inherent restlessness of empty space is not just a theoretical construct. Its effects are experimentally measurable, as famously demonstrated by the Casimir effect, where two uncharged parallel metal plates feel a subtle attractive force due to the differential pressure of these virtual particles. But the implications of this active vacuum extend far beyond the laboratory. Modern cosmology, particularly theories involving cosmic inflation, suggests that these minute quantum jitters in the very early universe, during an unimaginably rapid period of exponential expansion, were stretched and amplified to macroscopic scales. These tiny primordial fluctuations in the vacuum became the initial imperfections, the subtle variations in density that served as the gravitational seeds from which all the large-scale structures we observe today, galaxies, galaxy clusters, and the vast, intricate cosmic web, ultimately grew. Imagine a perfectly smooth, featureless canvas suddenly rippling with invisible vibrations, which then swell to become the grand mountains and sweeping valleys of a new world, forming the very architecture of the cosmos. This implies that the entire observable universe, with its intricate patterns of stars and galaxies, owes its very structured existence to the unpredictable, probabilistic dance of the quantum vacuum. We are, in a profound sense, the macroscopic manifestation of quantum randomness, a beautiful thought that connects our deepest origins to the fundamental uncertainties of reality. This quantum nature of space itself leads us back to the profound challenge of quantum gravity, the quest to unify Einstein's smooth, continuous spacetime, a tapestry of geometry, with the granular, probabilistic quantum world. While ambitious theories like string theory and loop quantum gravity offer different paths, they both hint at a universe where space-time itself is not a fixed, immutable stage, but a dynamic quantum entity. In these speculative frameworks, the very fabric of space and time might be composed of discrete, indivisible units at the incredibly tiny Planck scale, an unimaginably small length of approximately 10 to the minus 35 meters. Imagine, instead of a flowing river of space and time, that reality at its most fundamental level is a frothy, bubbling space-time foam, a chaotic quantum tapestry of constantly forming and dissolving loops, or networks. In this view, space is not infinitely divisible, but is comprised of fundamental atoms, or pixels, much like a digital image, where resolution has a limit. Time, too, might not be a continuous flow, but rather an emergent phenomenon arising from the dynamic rearrangement of these fundamental spatial units. This perspective fundamentally alters our understanding of reality, suggesting that the familiar smooth dimensions of space and the relentless linear march of time are but macroscopic approximations, elegant illusions that emerge from a deeper, more fragmented quantum reality. The universe, in this light, is not merely contained within space and time, but rather is space and time, constantly being woven and rewoven, a silent, intricate act of cosmic creation at every infinitesimal point. Delving further into the abstract, the concept of information itself appears to be deeply fundamental in the quantum realm, taking on properties far more profound than its classical counterpart. Unlike classical information, which can be copied and measured without altering the original, quantum information, encoded in delicate qubits, is famously fragile and cannot be perfectly cloned, a principle known as the no-cloning theorem. This is a direct consequence of quantum mechanics linearity, ensuring the inherent uniqueness of quantum states. Furthermore, one of the most perplexing puzzles in theoretical physics, the black hole information paradox, arises from the apparent loss of information when matter falls beyond a black hole's event horizon. According to the bedrock principles of quantum mechanics, information should never be truly lost, only scrambled or transformed. Stephen Hawking's groundbreaking discovery of black hole radiation, or Hawking radiation, suggested that black holes eventually evaporate, posing the critical question: what happens to the information of everything that fell into them once the black hole is gone? While a definitive solution remains elusive and hotly debated, some theories, most notably the holographic principle, propose that the information about the three-dimensional contents of a black hole, or indeed our entire universe, might be entirely encoded on a two-dimensional boundary surface. Imagine the universe not as a solid three-dimensional volume, but as a colossal hologram, where all the complex information of our perceived reality is projected from a simpler, two-dimensional bounding surface. This idea, while initially sounding like science fiction, has deep mathematical underpinnings in quantum gravity and string theory, suggesting that information is not merely a description of reality, but perhaps a fundamental constituent, conserved and intricately woven into its deepest fabric. Finally, we return to the most intimate and profound connection: the enduring relationship between quantum mechanics and consciousness. The measurement problem, with its perplexing observer effect and the enigmatic collapse of the wave function from a superposition of possibilities into a single, definite outcome, has historically led some thinkers to speculate about a direct, active role for consciousness in shaping quantum reality. While the prevailing view among mainstream physicists is that any interaction, whether by a conscious being or an inanimate detector, is sufficient to cause decoherence and collapse. The fundamental question of how consciousness itself arises from the purely physical interactions of billions of neurons remains the hard problem of neuroscience and philosophy. Some highly speculative theories, though lacking robust experimental evidence and facing significant challenges from the rapid onset of decoherence in warm, wet biological systems, nonetheless propose that quantum effects within the brain, such as quantum coherence or entanglement among microtubules or other intricate biological structures, might play a subtle but crucial role in the emergence of our subjective experience and awareness. While these ideas remain at the very frontier of scientific inquiry, they nonetheless invite a profound contemplation. Are we, as conscious beings, not merely passive observers of the quantum universe, but perhaps, in some subtle and intricate way, active participants in its fundamental unfolding? our minds mirroring the universe's own intricate dance of information and potentiality? This question, remaining largely unanswered, reminds us of the endless frontiers of knowledge and the beautiful, deeply personal mystery of our existence within this quantum cosmos. As we gently settle into the deeper realms of quantum understanding, having traversed the landscapes of fields, the Higgs mechanism, and the delicate dance of decoherence, we are left with questions that extend beyond mere scientific description, touching upon the very essence of reality and our place within it. The profound shift from a deterministic, classical universe to a probabilistic, quantum one compels us to reevaluate our most fundamental assumptions about existence, observation, and the nature of objective truth. This is perhaps the most enduring legacy of quantum mechanics. It forces us not just to learn new facts, but to think in entirely new ways about the universe. The very act of observation, as we discussed with wave function collapse, remains a central philosophical puzzle, while decoherence provides a practical explanation for why macroscopic objects appear classical. It does not fully resolve the deep question of how a system transitions from a superposition of all possibilities to a single, definite outcome. Does reality truly choose a path only when we look? Or is it a continuous objective process that simply appears instant from our limited perspective? Different interpretations. From the Copenhagen view, emphasizing our role as observers, to the many worlds interpretation suggesting a branching universe for every quantum choice, offer vastly different philosophical landscapes. What is undeniable, however, is that quantum mechanics has dissolved the neat boundary between the observer and the observed, implying an intricate, if subtle, connection between our consciousness and the unfolding of physical reality at its most fundamental level. This profound entanglement with the universe invites a quiet contemplation. Are we not just witnessing the cosmos, but somehow an integral part of its ongoing definition? The remarkable success of quantum field theory as the bedrock of the Standard Model underscores a deeper elegance in the universe's design. It tells us that what we perceive as discrete particles are, in fact, localized excitations of omnipresent fields. Electrons are ripples in the electron field, photons are quanta of the electromagnetic field, and even the elusive Higgs boson is an excitation of the Higgs field that imbues other particles with mass. This field-centric view provides a unified and consistent framework for understanding three of the four fundamental forces of nature. The mathematical symmetries underlying these fields dictate the very existence and behavior of the force-carrying particles, revealing a universe built upon principles of exquisite balance and invariance. It is a testament to the power of abstract thought, transforming seemingly disparate phenomena into a harmonious, interconnected symphony of fields and their vibrant excitations. This profound unity at the deepest level can evoke a sense of calm wonder, knowing that beneath the apparent chaos of the subatomic world lies an intricate and beautiful order. Yet, even this triumphant Standard Model has its limitations, leaving us with profound cosmic mysteries that continue to inspire future directions in quantum physics. The most glaring omission is gravity, which remains stubbornly outside the quantum fold. The quest for a theory of quantum gravity, whether through string theory's vibrating strings in extra dimensions or loop quantum gravity's granular spacetime, is an ongoing testament to humanity's relentless drive to unify all of nature's forces into a single, coherent description. But beyond gravity, the Standard Model also offers no explanation for the existence of dark matter and dark energy, which together constitute approximately 95% of the universe's total mass energy. These invisible components, whose gravitational and repulsive effects are clearly observed on cosmic scales, hint at a vast unseen quantum landscape, perhaps populated by new exotic particles or fields that lie beyond the current Standard Model's scope. The universe, in its quiet grandeur, continues to hold immense secrets, challenging us to expand our understanding beyond our current horizons, reminding us that knowledge is an endless frontier. This brings us to a contemplative reflection on the concept of emergent properties. Much like the classical world emerges from the decoherence of quantum states, so too do complex phenomena, such as life, consciousness, and the intricate structures of the universe, emerge from the underlying quantum rules. The fundamental constants of nature, the strength of the electromagnetic force, the mass of the electron, the value of Planck's constant, are all precisely tuned to allow for the formation of stable atoms, complex chemistry, and eventually the conditions necessary for life. If these constants were even slightly different, the universe as we know it would likely be barren and lifeless. This fine-tuning of the cosmos, while not directly explained by quantum mechanics alone, underscores the delicate balance inherent in the universe's deepest physical laws. It suggests that our existence is not merely a cosmic accident, but a profound consequence of the universe's fundamental quantum architecture, a symphony of precisely set parameters that allow for the intricate dance of matter and energy to unfold into self-aware beings capable of pondering their own quantum origins. And in this awareness we find a deep, tranquil connection to the grand, evolving story of the cosmos itself. The universe, in its intricate complexity, continues to whisper secrets, even as our understanding of the quantum realm has deepened profoundly. While the standard model of particle physics stands as a monumental triumph, accurately describing the fundamental particles and 3 of the 4 forces, it remains an incomplete picture. It leaves open some of the most profound questions about reality: the nature of dark matter and dark energy, the existence of gravity at the quantum scale, and the very structure of space-time at its most infinitesimal. These unanswered questions are not limitations, but rather beacons, guiding the next generation of physicists towards an even grander understanding, pushing the boundaries of what is known into the tranquil expanse of the unknown. One of the most compelling proposals for physics beyond the standard model is supersymmetry, often abbreviated as SUSY. This elegant theoretical framework suggests that for every known particle in the standard model, there exists a heavier superpartner particle. For example, the electron would have a superpartner called the selectron, and the photon would have a photino. These superpartners would differ from their standard model counterparts in their spin, a fundamental quantum property. If supersymmetry were indeed a true symmetry of nature, it would offer solutions to several perplexing problems. It could help explain why the Higgs boson, responsible for giving particles mass, is so much lighter than predicted by some theories, a puzzle known as the hierarchy problem. Furthermore, the lightest supersymmetric particle, often a neutralino, is a prime candidate for dark matter, the invisible substance that makes up about 27% of the universe's mass and influences the gravitational dynamics of galaxies. The search for these elusive superpartners is a major experimental undertaking, as their discovery would revolutionize our understanding of the universe's fundamental constituents. Imagine a hidden mirror world of particles quietly influencing our reality, waiting to be unveiled. This perspective offers a profound sense of the universe's hidden depths. Beyond individual particles, physicists also strive for a deeper unification of forces through grand unified theories, or GUTS. These theories propose that at incredibly high energies, far beyond anything we can currently achieve in laboratories, energies akin to those present moments after the Big Bang, the electromagnetic, weak and strong nuclear forces, which appear distinct in our everyday experience, might actually be different manifestations of a single, overarching fundamental force. Think of ice, water, and steam. They are distinct phases of the same substance, appearing very different at various temperatures. Similarly, GUTS suggests that these 3 forces converge into a single unified force at extremely high energies. This elegant concept implies a deeper simplicity and symmetry in the universe's fundamental laws. While experimental verification of GUTS remains challenging due to the immense energies required, indirect evidence, such as the precise values of the fundamental coupling constants and the proton's stability, offer tantalizing hints. The potential decay of the proton, a key prediction of many guts, is being meticulously searched for in vast underground detectors, awaiting a subtle signal that would confirm this grand unification. It is a profound quest for cosmic harmony, seeking the single melody from which all the universe's forces orchestrate their intricate dance. The pursuit of these theoretical frontiers is intrinsically linked to experimental endeavors, pushing the boundaries of technology and human ingenuity. Particle accelerators continue to be our most powerful microscopes, allowing us to probe the smallest scales and highest energies. Upgrades to the Large Hadron Collider, for instance, aim to increase its collision energy and luminosity, enhancing its ability to discover new particles and forces, or to precisely measure the properties of known ones. Beyond accelerators, a global network of experiments is dedicated to detecting dark matter particles directly, often deep underground to shield them from cosmic rays. These detectors hope to observe the rare, faint interaction of a dark matter particle with ordinary matter, revealing its true nature. Meanwhile, neutrino experiments studying these elusive, nearly massless particles continue to unveil their mysterious properties, including their ability to oscillate between different flavors. The universe, as we perceive it in our everyday lives, often appears as a continuous, unbroken canvas, a flowing tapestry where quantities like energy and motion seem to vary without limit. Yet, as the 19th century drew to a close and the 20th began, physicists encountered a series of perplexing phenomena that stubbornly defied these classical explanations, hinting at a deeper, more granular reality beneath the surface of appearances. It began, quite unexpectedly, with the seemingly innocuous problem of black body radiation, the characteristic spectrum of light emitted by any object solely due to its temperature. Imagine a piece of hot metal glowing red, then orange, then white as it gets hotter. Classical physics, with its elegant equations, predicted an unsettling anomaly, the ultraviolet catastrophe. This theory suggested that an ideal hot object should emit an infinite amount of energy at very short wavelengths, like ultraviolet light and beyond, which was demonstrably not observed in experiments. The universe simply did not behave that way, leaving a gaping wound in the heart of classical physics. It was Max Planck, in the year 1900, who introduced a revolutionary, almost desperate hypothesis to resolve this glaring paradox. He proposed, with a degree of reluctance at first, that energy is not emitted or absorbed continuously, like water flowing from a tap, but rather in discrete, indivisible packets, which he termed quanta. To grasp this, consider an analogy. Imagine trying to climb a perfectly smooth, continuous ramp. Classical physics suggested you could rest at any infinitesimal height. Planck, however, suggested that energy was more akin to a staircase, where you can only stand on specific, distinct steps, and cannot exist anywhere in between them. Each step represents a quantum of energy, and its size, its magnitude, is directly proportional to the frequency of the radiation, scaled by a truly fundamental constant, now universally known as Planck's constant, or simply h. This incredibly tiny, yet profoundly significant number represents the smallest possible unit of action in the universe, a kind of indivisible currency of reality at its most fundamental level. This was not merely a convenient mathematical trick to make the equations fit the experimental data. It was a radical shift in perspective, suggesting for the first time that the very fabric of energy itself possessed a fundamental granularity, a kind of atomic structure, much like matter. This audacious notion of energy existing in discrete packets found further, even more compelling, empirical support with Albert Einstein's brilliant explanation of the photoelectric effect in 1905. This phenomenon involves light shining on certain metals, causing them to eject electrons. Classical wave theory, which had successfully described many aspects of light, predicted that the energy of these ejected electrons should depend primarily on the intensity of the incident light, and that any frequency of light, given enough intensity and time, should eventually dislodge electrons. Yet, meticulous experiments consistently showed otherwise. Electrons were only ejected if the light's frequency was above a certain critical threshold, regardless of how intense or bright the light source was. Below that specific frequency, no electrons were emitted, no matter how long the light shone or how powerful its beam. Einstein, with characteristic insight, built upon Planck's pioneering idea and proposed that light itself consists of individual discrete packets of energy, which he initially called light quanta, and which we now famously refer to as photons. Each photon, he posited, carried a specific amount of energy directly proportional to its frequency. If a single photon did not possess enough energy, that is, if its frequency was too low, it simply could not knock an electron free from the metal, regardless of how many such low-energy photons struck the surface. Conversely, if a single photon had sufficient energy, it could instantly eject an electron, even if only a few such high-energy photons were striking the material. This groundbreaking insight not only explained the photoelectric effect perfectly, but also provided undeniable evidence that light, which had been understood purely as a wave phenomenon for centuries, also exhibited undeniable particle-like behavior. And here, dear listener, we encounter the first truly profound and perhaps the most counterintuitive mystery of the quantum world: wave-particle duality. Light, which we experience and model so successfully as waves. Think of the shimmering, continuous patterns on a pond's surface, or the elegant way colors separate and blend in a rainbow or a prism, also manifests as distinct localized particles, these discrete photons. It is not a choice between one or the other, it is both, simultaneously maintaining these seemingly contradictory natures. This duality is not merely an abstract philosophical concept, it is the fundamental bedrock of how light interacts with matter and energy at the quantum scale. The universe, in its intricate and subtle wisdom, seems to utilize both aspects depending on the specific circumstances, weaving an eternal and complex dance between continuous flow and discrete packets. It is a reminder that our macroscopic intuition, formed by observing large objects, often falls short when we delve into the infinitesimal. But the quantum revelations, as you might imagine, did not stop with light. The stage was set for an even more audacious leap. Louis de Broglie, a French physicist in 1924, extended this radical idea to matter itself. He hypothesized in his doctoral thesis that if light waves could behave like particles, then perhaps particles of matter, such as electrons, protons, and indeed all fundamental constituents of the universe, could also exhibit wave-like properties. This was an astonishing claim, for we typically observe electrons as distinct, localized particles within atoms, much like tiny planets orbiting a central sun, though that classical image is itself an oversimplification. Yet, de Broglie proposed that every particle has an associated wavelength, now known as the de Broglie wavelength, which is inversely proportional to its momentum. This means that the heavier an object and the faster it moves, the shorter its de Broglie wavelength becomes, rendering its wave nature utterly imperceptible in our everyday macroscopic world. This is precisely why we do not perceive ourselves, or a thrown baseball, or even a grain of sand, as waves. Our wavelengths are infinitesimally, immeasurably small, far beyond any detection. This theoretical leap, initially met with skepticism, was soon confirmed experimentally in 1927 by American physicists Clinton Davison and Lester Germer, and independently by George Paget Thomson in Scotland. They observed electrons diffracting, or spreading out in a wave-like pattern, when fired at a nickel crystal. Just as X-rays, a well-known form of electromagnetic wave, diffract when passing through a crystal lattice, creating distinct interference patterns, so too did these streams of electrons. This profound discovery cemented the idea that matter, at its most fundamental level, is also dualistic. An electron is not simply a tiny billiard ball with a definite position and trajectory. It is also, simultaneously, a spread-out wave of probability. And this wave doesn't just describe where the electron might be. In a profound sense, it describes the electron itself before it is definitively measured or forced into a particular state. This inherent wave-like nature of matter profoundly changes our most fundamental understanding of reality. It means that the basic building blocks of everything around us, and indeed within us, every atom, every molecule, every cell, are not solid, distinct points, but rather fuzzy, extended probability distributions. When you consider the solidity of the chair you might be resting in, or the very atoms that compose your hand, they are not fixed, definite entities in the classical sense. Instead, they are manifestations of these underlying wave functions poised between possibilities until an interaction, an observation, brings them into a concrete state. This is not a weakness or an incompleteness of our understanding, but rather a profound intrinsic feature of nature itself. The universe, at its core, is a dynamic realm of potential and probability, where the familiar solidity and definiteness of objects emerge from the collective behavior of countless unseen waves. It is a beautiful, if unsettling, realization that even our own existence is fundamentally tied to these quantum uncertainties. This initial foundational insight into quantization and wave-particle duality lays the essential groundwork for the deeper mysteries we are yet to explore, gently guiding us towards a reality far richer, more intricate, and more wonderfully strange than our everyday senses alone might ever suggest. As we gently drift deeper into the quantum realm, having encountered the strange duality of waves and particles, we find ourselves needing a new language, a new way to describe this profoundly different reality. The classical world, with its precise trajectories and predictable outcomes, simply cannot capture the inherent fuzziness and probabilities that govern the smallest constituents of existence. This is where the concept of the wave function emerges, a central pillar of quantum mechanics. Imagine, if you will, that every particle, be it an electron, a photon, or even a proton, is not merely a tiny, hard sphere, but rather a spread-out cloud of potential existing across a region of space. The wave function, often denoted by the Greek letter psi or pex, is the mathematical entity that precisely describes this cloud, encoding all the information we can possibly know about a quantum system. It doesn't tell us exactly where a particle is, but rather where it is likely to be. This probabilistic interpretation, famously formulated by Max Born, suggests that the square of the magnitude of the wave function at any point in space gives us the probability of finding the particle at that specific location if we were to perform a measurement. It is not that the particle is at multiple places simultaneously, but rather that its existence is fundamentally undefined across a range of possibilities until an interaction forces it to manifest in a single, definite spot. Think of it less as a physical wave spreading through space and more as a wave of information, a potential landscape for the particle's presence. Before observation, the particle is, in a profound sense, smeared out across all its possible locations, a cloud of likelihoods. This shifts our understanding from a universe of definite things to one of probabilities and potentials, a subtle yet monumental change in perspective. And as we consider this, we might wonder, does our own presence, our own consciousness, play an active role in shaping the reality we perceive from this sea of possibilities? The evolution of this mysterious wave function is governed by another cornerstone of quantum theory, the Schrödinger equation. Developed by Erwin Schrödinger in 1926, this mathematical equation acts as the quantum world's equivalent of Newton's laws of motion. While Newton's laws predict the precise trajectory of a billiard ball, the Schrödinger equation predicts how the probability distribution of a quantum particle changes over time. It is a deterministic equation, meaning that if you know the initial wave function of a system, you can, in principle, calculate its wave function at any future moment with absolute certainty. However, the outcome of any specific measurement on that system remains inherently probabilistic. The equation doesn't tell us where an electron will land, but rather the probabilities of it landing in various places. This fundamental difference marks a profound departure from classical physics, where perfect knowledge of initial conditions would lead to perfect prediction of all future states. The Schrödinger equation also elegantly explains the existence of quantized energy levels within atoms. Just as Planck first proposed that energy comes in discrete packets, the solutions to the Schrödinger equation for particles confined within a potential well, like electrons bound to an atomic nucleus, reveal that they can only occupy specific, discrete energy states. They cannot possess any energy value in between these allowed levels. This is why atoms emit and absorb light only at very specific wavelengths, leading to their unique spectral fingerprints. Imagine a musical instrument that can only play certain notes, never sliding between them. Atomic electrons are much the same, jumping between these distinct energy steps as they absorb or emit photons. This quantization of energy is a direct observable consequence of the wave-like nature of matter confined within a small space, profoundly shaping the stability and chemical properties of all elements, and indeed the very structure of the universe around us. This leads us directly to the perplexing concept of superposition. If a quantum system can be described by a wave function that encompasses multiple possibilities, then, before measurement, the system exists in a superposition of all those possible states simultaneously. For instance, an electron might exist in a superposition of spin up and spin down at the same time, or be in a superposition of being in two different locations simultaneously. This is not a matter of it rapidly switching between states or of our ignorance about its true state. Rather, it is genuinely existing in all these states at once, a blurred reality of coexisting possibilities. The famous thought experiment of Schrödinger's cat, locked in a box with a quantum trigger that might or might not release a deadly poison, vividly illustrates the apparent absurdity when we try to scale this quantum behavior to the macroscopic world. According to quantum mechanics, until the box is opened, the cat is in a superposition of being both alive and dead. Of course, in practice, a cat is a macroscopic system constantly interacting with its environment, which acts as a continuous measurement, rapidly collapsing any such superposition. But for isolated microscopic particles, this simultaneous existence of multiple states is a fundamental truth. The moment we interact with a quantum system to determine its state, the act of measurement, is when this superposition vanishes. The wave function, which described all the potential states, collapses into a single, definite outcome. The electron that was suddenly registers as either spin up or spin down. The particle that was spread out across a region is now found at a single point. This process of wave function collapse remains one of the most enigmatic and debated aspects of quantum mechanics. What constitutes a measurement? Does it require a conscious observer, or is any interaction with the environment sufficient? Different interpretations of quantum mechanics offer varying perspectives. Our journey into quantum mechanics begins by acknowledging a fundamental truth. The universe, at its smallest scales, does not behave in ways our everyday intuition can easily grasp. For centuries, our understanding of reality was built upon the familiar principles of classical physics, where objects have definite positions, clear trajectories, and predictable interactions. We see a ball, we throw it, and we can calculate precisely where it will land. But when we descend into the realm of atoms and their constituent particles, electrons, photons, quarks, this comforting predictability dissolves. Here, at the very bedrock of existence, the rules change dramatically, revealing a world of inherent uncertainty, strange dualities, and interconnectedness that challenges our deepest assumptions about what is real. This is not a failure of our understanding, but rather a profound revelation about the universe itself, a glimpse into its most intricate and perplexing secrets. One of the most mind-bending aspects of this microscopic domain is what physicists call wave-particle duality. For generations, scientists debated whether light was a wave or a stream of particles. Isaac Newton saw particles, while Christian Huygens championed waves. It took the revolutionary work of thinkers like Max Planck and Albert Einstein to show that light, in fact, exhibits characteristics of both. Light, when traveling, acts like a wave, creating interference patterns, much like ripples on a pond. Yet, when it interacts with matter, such as being absorbed by an atom, it acts like discrete packets of energy, which we call photons. Each photon is a distinct particle. So, light isn't simply one or the other, it possesses this dual nature. But the strangeness does not end with light. Louis de Broglie, a brilliant French physicist, later proposed that this duality applies not just to light, but to all matter. Electrons, protons, even entire atoms, while typically thought of as solid particles, also possess wave-like properties. Imagine this: the very building blocks of your body, the electrons forming your atoms, are not just tiny hard spheres, but also diffuse extended waves of probability. This concept is central to understanding how the quantum world operates, forcing us to abandon our classical notions of what a thing truly is. To truly appreciate this duality and the peculiar nature of quantum reality, we must turn to perhaps the most iconic experiment in all of physics, the double-slit experiment. It is deceptively simple in its setup, yet profoundly unsettling in its implications. Imagine a screen with two narrow vertical slits cut into it. Behind this screen, we place a detector that can record where particles land. Now, if we were to fire ordinary macroscopic objects, like tiny marbles, one by one at this barrier, what would we expect to see? Naturally, the marbles would either go through the left slit or the right slit, creating two distinct bands of impact points on the detector screen directly behind each slit. This is precisely what classical physics predicts for particles. However, when we perform this experiment with quantum particles, such as electrons, the results are astonishingly different. If we fire a stream of electrons, one at a time, what appears on the detector screen is not two distinct bands, but rather an interference pattern, a series of bright and dark fringes, exactly what one would expect if waves were passing through both slits and interfering with each other. This suggests that each individual electron, despite being sent one at a time, somehow behaves like a wave, passing through both slits simultaneously and interfering with itself before landing at a single point on the screen. It is as if the electron explores all possible paths at once. But the experiment takes an even stranger turn. What happens if we try to observe which slit the electron actually passes through? If we place a detector at one of the slits to gather this information, something remarkable occurs. The interference pattern vanishes. Instead, we once again see two distinct bands, just as if we were firing classical marbles. The act of measurement, the very attempt to gain knowledge about the electron's path, forces it to behave like a particle, to choose a single path, and the wave-like behavior disappears. This phenomenon is often referred to as the collapse of the wave function, where the electron's state of existing in multiple possibilities collapses into a single, definite outcome upon observation. It is a profound demonstration that at the quantum level, reality is not fixed until it is observed. The universe seems to keep its options open, existing in a state of blurred probabilities, until an interaction or a measurement forces a choice. This is not to say that consciousness is required, as any interaction with the environment, even an inanimate detector, can cause this collapse. But it does imply that the familiar, solid, definite world we perceive is an emergent property, a consequence of countless quantum interactions settling into specific states. This leads us directly to the concept of superposition, a cornerstone of quantum mechanics. Superposition describes the ability of a quantum system to exist in multiple states simultaneously until it is measured. Imagine a quantum coin that is both heads and tails at the same time. It is not one or the other, but a combination of both possibilities existing in a probabilistic haze. Only when you look at it, when you force a measurement, does it decide to be either heads or tails. In the context of the double-slit experiment, the electron is in a superposition of going through the left slit and going through the right slit until its path is observed. This isn't merely a lack of information on our part, it is a fundamental property of the quantum entity itself. The electron truly is, in a very real sense, exploring all potential realities until a specific interaction forces it to commit to one. This inherent uncertainty is not a flaw in the theory, but a defining characteristic of the micro-world. It means that the fundamental nature of reality is probabilistic rather than deterministic. For us living in the macro-world, this seems counterintuitive, almost like magic. But for the tiny constituents of the universe, it is simply how things are. This profound insight, first grappled with by pioneers like Werner Heisenberg and Erwin Schrödinger, forever changed our understanding of existence. It suggests that the reality we experience with its distinct objects and clear events is merely one of many potential realities that could have unfolded. And when we contemplate this, the idea that the very fabric of our being is constructed from particles that exist in such a fluid, uncertain state, it can evoke a profound sense of true wonder. This notion of superposition is not just a theoretical curiosity, it is a mathematical necessity within the framework of quantum theory. Particles are not simply tiny billiard balls, they are described by wave functions, which are mathematical expressions that encapsulate all the possible states a particle can be in, along with the probabilities of finding it in each of those states. It's like a whisper of all potential futures, all existing simultaneously until the moment of observation. Erwin Schrödinger famously illustrated this paradox with his thought experiment involving a cat in a sealed box, simultaneously alive and dead until the box is opened. While a macroscopic cat never truly exists in such a state, the experiment highlights the bizarre consequences of applying quantum rules to our everyday world and emphasizes the difficulty in reconciling the quantum and classical realms. It serves as a stark reminder that our common sense, honed by interactions with large objects, is simply inadequate for grasping the nuanced behavior of the very small. Furthermore, this quantum weirdness extends beyond individual particles. The entire universe, at its most fundamental level, can be thought of as a collection of quantum fields. These fields are not empty space, but rather energetic entities that permeate everything. Particles, in this view, are not distinct little entities, but rather localized excitations or ripples within these fields. An electron is a ripple in the electron field, a photon is a ripple in the electromagnetic field, and so on. This perspective, known as quantum field theory, provides a more complete and elegant description of the subatomic world. It implies that even in what we perceive as empty vacuum, these fields are constantly fluctuating, giving rise to virtual particles that momentarily pop into existence and then vanish, too fleeting to be directly observed, but leaving measurable effects. This constant, restless activity in the vacuum of space underscores that nothingness is far from inert. It is a vibrant, bubbling cauldron of potential. The implications for our understanding of reality are vast. If everything is fundamentally probabilistic, if particles only assume a definite state upon measurement, then the very foundation of what we consider real shifts. It suggests that the objective reality we perceive is not entirely independent of our interaction with it. This isn't to say that the moon isn't there when no one is looking, a common misconception. Rather, it means that its constituent particles exist in a spectrum of possibilities until they interact with something, or until information about them is obtained. The universe, in a sense, is a grand, unfolding story where the details are filled in as events transpire, rather than a fixed tapestry already completed. This profound concept has led to various interpretations of quantum mechanics, each attempting to make sense of this inherent strangeness. From the Copenhagen interpretation, which posits that the wave function simply collapses, to the many worlds interpretation, which suggests that every quantum measurement causes the universe to split into multiple parallel realities, each representing a different possible outcome. While these interpretations offer different frameworks, they all agree on the observational facts. The quantum world is fundamentally non-classical, unpredictable in its precise outcomes, and deeply probabilistic. Consider the precision required for our modern technologies. Lasers, semiconductors, even the very digital devices through which you are listening to this. All of these rely on our understanding and manipulation of quantum phenomena, the stability of atoms, the way chemical bonds form, the very existence of matter as we know it, are all governed by these peculiar quantum rules. Without the Pauli exclusion principle, for instance, which states that no two identical quantum particles can occupy the same quantum state simultaneously, all electrons would collapse into the lowest energy level, and atoms would cease to have structure, making chemistry and life impossible. So, while quantum mechanics might seem abstract and distant, its principles are intimately woven into the fabric of our everyday existence, silently underpinning the stability and diversity of the world around us. It is this intricate dance of probabilities and interactions that allows for the emergence of complex structures, from the simplest hydrogen atom to the intricate neural networks within your own brain. And as we settle into the quiet contemplation of this micro-world, we might find a peculiar comfort in its inherent uncertainty. Just as the universe at large is a vast expanse of unknown possibilities, so too are the smallest components of reality a testament to the fact that existence is far richer and more nuanced than our direct senses reveal. The idea that everything around us, and indeed within us, is a continuous interplay of probabilities, constantly shifting and coalescing, invites us to release the need for absolute certainty and embrace the quiet mystery of being. Perhaps in understanding the fluid nature of reality at its core, we can find a deeper sense of peace, knowing that our own existence, with its myriad choices and paths, is a beautiful echo of the quantum dance that underpins everything. The strange dance of quantum particles, where states remain undefined until measured, leads us to yet another profound and perhaps even more perplexing phenomenon: quantum entanglement. If the idea of a particle existing in multiple places at once feels counterintuitive, then entanglement will stretch our understanding of reality even further. Imagine two particles, perhaps two photons or two electrons, that interact in a specific way. After this interaction, they become intrinsically linked, or entangled. What this means is that their fates are intertwined, no matter how far apart they are separated in space. If you measure a property of one entangled particle, such as its spin or polarization, you instantly know the corresponding property of the other particle, even if it is light years away. This connection appears to happen instantaneously, seemingly defying the cosmic speed limit set by Albert Einstein's theory of relativity. Einstein himself, along with his colleagues Boris Podolsky and Nathan Rosen, found this concept so unsettling that they famously dubbed it spooky action at a distance. They believed it pointed to a fundamental incompleteness in quantum mechanics, suggesting that there must be hidden variables, some underlying information that predetermines the outcomes of these measurements, thus preserving classical realism and locality. However, a brilliant physicist named John Stuart Bell later formulated a theorem that provided a way to experimentally test whether such hidden variables could truly explain entanglement. Subsequent experiments, notably those by Alain Aspect and his team in the 1980s, conclusively demonstrated that the correlations observed between entangled particles are stronger than any classical theory, allowing for local hidden variables, could explain. The spooky action, it turns out, is real. It is a fundamental feature of the quantum universe, not an illusion or a gap in our knowledge. This profound interconnectedness, where particles share a common destiny irrespective of spatial separation, has no analog in our everyday world. There is no classical way to explain how two objects could instantly communicate their states without any physical interaction or signal passing between them. It compels us to rethink the very nature of reality, suggesting that at the deepest level, the universe is not merely a collection of isolated particles, but a vast, interconnected web of quantum relationships. This is not about information traveling faster than light. Rather, the particles are part of a single, unified quantum system. Their individual properties are not determined until measured, and that measurement instantly defines the state of both. This seemingly magical link is not used for transmitting classical information faster than light, but it opens doors to revolutionary technologies such as quantum communication, offering potentially unbreakable encryption, and quantum computing, where qubits, quantum bits, can leverage both superposition and entanglement to perform calculations far beyond the capabilities of classical computers. Building on this, the quantum world also presents us with the astonishing phenomenon of quantum tunneling. In classical physics, if a ball doesn't have enough energy to roll over a hill, it simply won't make it to the other side. It will roll back down. Barriers are absolute. But at the quantum scale, particles can, with a certain probability, tunnel right through an energy barrier, even if they do not possess sufficient energy to overcome it classically. It is as if they briefly borrow energy from the vacuum, or perhaps in their wave-like form, their probability wave simply extends through the barrier. While the probability of any single particle tunneling might be small, for countless particles, it becomes a regular occurrence. This seemingly impossible feat is not merely theoretical. It is a well-established quantum effect with profound implications. Quantum tunneling is, in fact, essential for life as we know it. Consider the sun and other stars. Their immense energy comes from nuclear fusion, where hydrogen nuclei fuse to form helium. However, atomic nuclei, being positively charged, naturally repel each other due to the electromagnetic force. Classically, the temperatures and pressures in the sun's core are not nearly high enough for protons to overcome this electrostatic repulsion and fuse. But thanks to quantum tunneling, a small fraction of these protons can effectively tunnel through this repulsive barrier, allowing fusion to occur. Without this quantum phenomenon, the sun would not shine, and the universe would be a very different, much colder, and indeed, lifeless place. Beyond stellar processes, quantum tunneling is harnessed in technologies like scanning tunneling microscopes, which can image individual atoms by exploiting the tunneling of electrons, and it explains radioactive decay, where particles spontaneously tunnel out of unstable atomic nuclei. It is a quiet, invisible process, yet its consequences are immense and deeply woven into the fabric of the cosmos. And as we delve deeper into these strange behaviors, we encounter another fundamental principle that underpins the quantum realm: Werner Heisenberg's uncertainty principle. This principle states that there are certain pairs of properties of a quantum particle, such as its position and its momentum, that cannot both be known with perfect precision simultaneously. The more precisely you measure one, the less precisely you can know the other. This is not a limitation of our measuring instruments, nor a matter of clumsy observation disturbing the system, though that does happen. Rather, it is an inherent, irreducible fuzziness built into the very nature of reality at its most fundamental level. It's as if the universe itself has a built-in limit to what can be known about its smallest constituents. Imagine trying to precisely locate a ripple on a pond while also knowing its exact direction and speed. By trying to pinpoint its position, you disturb its motion. By trying to define its motion, you lose its precise location. This principle extends to other pairs of complementary properties, such as energy and time. A particle can briefly borrow energy from the vacuum as long as it pays it back within a very short time. The shorter the time interval, the greater the amount of energy that can be borrowed. This allows for the fleeting existence of those virtual particles we discussed earlier. constantly popping in and out of existence in seemingly empty space. The uncertainty principle paints a picture of a universe that is not a perfectly defined machine, but rather a dynamic, subtly blurred tapestry of probabilities. It means that at the very root of all existence, there is an irreducible element of chance, an inherent unpredictability that defies deterministic prediction. This profound insight forces us to reconsider our classical notions of cause and effect, suggesting that some events are truly random, not just due to our lack of information. And when we reflect on this, the idea that the universe, even at its core, holds a graceful inherent uncertainty. It can bring a quiet sense of wonder, allowing us to find peace in the unknown, much like drifting into a tranquil sleep. We have journeyed through the realm where particles exist in multiple states and are mysteriously linked across vast distances. Now, let us consider the deeper tapestry from which these phenomena emerge, the concept of quantum fields. Our everyday perception often leads us to imagine particles as tiny, discrete balls, like miniature marbles. However, modern physics, particularly quantum field theory, offers a more profound and elegant perspective. It suggests that the universe is not fundamentally made of particles, but rather of fields that permeate all of space and time. These fields are not static or empty. Instead, they are dynamic, vibrant entities, constantly fluctuating even in what appears to be a perfect vacuum. Particles, in this view, are not fundamental objects themselves, but rather localized excitations or tiny ripples in these underlying quantum fields. Imagine a vast, calm ocean. A particle is not a distinct drop of water, but a momentary wave, a disturbance that travels across its surface. Every type of fundamental particle we know, electrons, photons, quarks, corresponds to a specific quantum field. An electron, for instance, is an excitation in the electron field, and a photon is a quantum of the electromagnetic field. This perspective allows us to reconcile the wave-particle duality we discussed, as particles are both wave-like, as fields, and particle-like, as localized excitations. This grand framework of quantum fields forms the bedrock of what we call the Standard Model of particle physics. The Standard Model is our most successful theory describing the fundamental particles and forces that govern the universe, excluding gravity. It categorizes matter particles, known as fermions, such as quarks and leptons, which include electrons and neutrinos. These are the building blocks of all ordinary matter. Then there are force-carrying particles called bosons, which mediate the fundamental interactions. For example, photons carry the electromagnetic force, which is responsible for light, electricity, and magnetism, and holds atoms together. Gluons carry the strong nuclear force, binding quarks together within protons and neutrons, and holding atomic nuclei intact. The W and Z bosons mediate the weak nuclear force, responsible for radioactive decay and nuclear fusion processes that power stars. This model is a triumph of human intellect, painstakingly developed over decades by countless scientists, uniting seemingly disparate phenomena under a single, coherent set of mathematical principles. It tells us that the universe, at its deepest level, is a symphony of interacting fields, a continuous hum of potentiality from which all reality emerges. Within this intricate standard model, one particular field holds a unique and crucial role in shaping the universe as we perceive it: the Higgs field. For many years, physicists grappled with a perplexing question: why do some fundamental particles have mass, while others, like the photon, appear to be massless? The answer, according to the Standard Model, lies with the Higgs field, an invisible energy field that pervades all of space. Imagine walking through a swimming pool filled with treacle or thick syrup. Some particles, those that interact strongly with the Higgs field, experience a greater drag or resistance as they move through it, much like walking through treacle. This resistance is what we perceive as mass. Particles that interact weakly with the Higgs field acquire less mass, and those that do not interact with it at all, like photons, remain massless, gliding unimpeded through the cosmic treacle. This interaction with the Higgs field is not a force in the traditional sense, but a fundamental property of how particles acquire their inertia, their resistance to changes in motion. The existence of the Higgs field was a theoretical prediction for decades, a missing piece in the Standard Model. It was hypothesized by Peter Higgs and several other physicists in the 1960s. The experimental confirmation of the Higgs boson, the particle associated with the Higgs field, at the Large Hadron Collider in 2012 was a monumental achievement in physics, a crowning moment that validated the Standard Model and deepened our understanding of the origin of mass. This discovery revealed that mass is not an inherent quality of particles, but rather a consequence of their interaction with this ubiquitous, all-pervading field. It means that the very solidity and substance of everything around us, including our own bodies, is a manifestation of these subtle, constant interactions with the Higgs field. We are, in a very real sense, continually immersed in this field, and its presence defines one of the most fundamental properties of our physical existence. This elegant mechanism provides a gentle yet profound explanation for why the universe has structure, why stars and galaxies can form, and why we, as beings with mass, can exist within it. As we contemplate these quantum fields and their intricate interactions, a natural question arises. If the micro-world is so strange, filled with superposition and entanglement, why do we not observe these phenomena in our everyday macroscopic lives? Why does the moon appear to be in a definite location, rather than a blur of possibilities? The answer lies in a process known as quantum decoherence. Decoherence is the mechanism by which quantum systems lose their quantum properties and begin to behave classically. It occurs when a quantum system interacts with its environment. At the microscopic scale, isolated particles can maintain their delicate quantum states, like superposition, for a fleeting moment. However, in our macroscopic world, systems are constantly interacting with an immense number of particles in their surroundings: air molecules, photons, thermal vibrations. Each of these interactions acts as a measurement, however indirect, forcing the quantum system to collapse from a superposition of states into a single, definite, classical state. Imagine our quantum coin simultaneously heads and tails. If it is perfectly isolated, it remains in this superposition. But if it interacts with even a single air molecule, that interaction essentially observes it, forcing it to choose either heads or tails. The more complex a system, and the more it interacts with its environment, the faster decoherence occurs. For something as large as a human being, with countless atoms constantly interacting with the environment, decoherence happens almost instantaneously, making it impossible to observe ourselves in a quantum superposition. This continuous interaction with the environment effectively erases the quantum weirdness, smoothing out the probabilities into the distinct classical reality we experience. So, the classical world is not separate from the quantum world. It emerges from it through this constant process of decoherence. It is a beautiful reconciliation, explaining how the baffling rules of the micro-world give rise to the reassuringly stable and predictable macro-world we inhabit. It's a gentle reminder that the universe has a way of organizing itself, allowing for both profound mystery at its core and tangible reality on its surface. We have journeyed through the realms of wave-particle duality, the perplexing double-slit experiment, and the profound interconnectedness of entanglement, all emerging from the vibrant tapestry of quantum fields. Now, let us consider the subtle yet immensely powerful energy inherent in what we often perceive as empty space. In classical physics, a vacuum is simply nothingness, a void devoid of matter and energy. However, quantum mechanics paints a far more dynamic picture. Even in the absence of any particles or radiation, the quantum fields we discussed earlier are never truly at rest. They are constantly fluctuating, bubbling with activity, giving rise to what are known as virtual particles. These particles, pairs of matter and antimatter, spontaneously pop into existence for an infinitesimally brief moment, only to annihilate each other and vanish back into the quantum foam. They are too fleeting to be directly observed, yet their transient existence has real, measurable effects, such as the Casimir effect, where two uncharged parallel metal plates placed very close together in a vacuum will actually experience a slight attractive force. This force arises from the subtle differences in the quantum fluctuations between the plates compared to those outside, demonstrating that empty space possesses an intrinsic energy, often referred to as vacuum energy. This vacuum energy is not merely a curiosity of the micro-world. Its implications extend to the largest scales of the cosmos. Scientists believe that this inherent energy of space might be intimately connected to the phenomenon of dark energy, the mysterious force responsible for the accelerating expansion of our universe. The cosmological constant, a term originally introduced by Albert Einstein into his equations of general relativity, but later famously retracted, has found a potential modern interpretation as a manifestation of this vacuum energy. While there is still a significant discrepancy between the theoretical predictions of vacuum energy and the observed strength of dark energy, the very idea suggests a profound link between the quantum realm and the large-scale structure and evolution of the universe. It hints that the expansive cosmic ballet we observe, with galaxies drifting ever further apart, might be gently orchestrated by the ceaseless, imperceptible activity of the quantum vacuum itself. The universe, then, is not expanding into a void of nothingness, but rather the nothingness itself is expanding, fueled by its own latent quantum energy, a concept that invites a deep, quiet contemplation of existence. This ability of quantum particles to exist in multiple states simultaneously and to be profoundly linked through entanglement is not merely a theoretical construct for physicists to ponder. It is being actively harnessed and engineered to develop revolutionary new technologies, most notably in the field of quantum computing. Unlike classical computers, which store information in bits that can only be either a 0 or a 1, quantum computers utilize quantum bits, or qubits. A qubit, thanks to the principle of superposition, can be both a 0 and a 1 simultaneously. This allows a quantum computer to process vast amounts of information in parallel, exploring multiple possibilities at once. Furthermore, when qubits are entangled, their fates become linked, meaning that the state of one instantly influences the state of others, regardless of distance. This entanglement allows for incredibly complex calculations and correlations between qubits that are impossible for classical systems to replicate. Imagine a symphony where each musician can play all notes at once and their instruments are mysteriously linked, instantly resonating with each other. This is the power that superposition and entanglement bring to quantum computation. While still in its nascent stages, quantum computing promises to revolutionize fields ranging from medicine and material science to cryptography and artificial intelligence. For instance, designing new drugs or materials often involves simulating complex molecular interactions, a task that quickly overwhelms even the most powerful classical supercomputers. Quantum computers, with their ability to model quantum phenomena directly, could unlock breakthroughs in these areas, allowing us to engineer substances with unprecedented properties or develop highly targeted therapies. In cryptography, quantum algorithms could break many of the encryption methods currently used to secure our digital communications, while simultaneously offering new, quantum-safe encryption techniques that are theoretically unbreakable. The development of quantum computers is a testament to the profound practical implications of understanding the subtle laws governing the micro-world, transforming what once seemed like abstract philosophical puzzles into tools that could reshape our future in profound, yet often quietly unfolding ways. Yet, despite these incredible advancements and applications, the quantum world continues to present us with fundamental puzzles, perhaps none more enduring than the measurement problem. We have already touched upon how observation causes the collapse of a quantum system's wave function, forcing it into a definite state. But what precisely constitutes a measurement? And does the act of observation imply a role for consciousness? While most physicists agree that any irreversible interaction with the environment, even by an inanimate detector, is sufficient to cause decoherence and collapse, the deeper philosophical questions persist. Different interpretations of quantum mechanics offer varying perspectives, each attempting to provide a coherent narrative for this perplexing aspect of reality. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggests that quantum systems simply do not possess definite properties until they are measured, and that measurement fundamentally alters the system. The many worlds interpretation, on the other hand, proposes with all outcomes being equally real. These are not just scientific theories, but profound reflections on the nature of reality itself. These ongoing debates highlight that even with our advanced understanding, the quantum realm retains an intrinsic mystery. It reminds us that our models and theories, while incredibly powerful and predictive, are still human constructs attempting to describe a reality that may ultimately transcend our intuitive grasp. The quest to fully comprehend the measurement problem and to reconcile quantum mechanics with the other great pillar of modern physics, general relativity, continues to drive scientific exploration. The search for a theory of quantum gravity, one that can seamlessly describe the universe at both the smallest quantum scales and the largest cosmic scales, remains one of the greatest challenges in physics. It is a testament to the boundless nature of inquiry, to the human spirit's relentless desire to understand the fundamental truths of existence. And perhaps in this ongoing journey of discovery, in the humble acceptance of what remains unknown, we find a tranquil beauty, a profound sense of awe that allows our minds to drift gently into the quiet expanse of the night, knowing that the universe holds secrets far grander than we can yet imagine, and that we are a part of this unfolding mystery. The profound mysteries of quantum mechanics, from the unsettling implications of the double-slit experiment to the instantaneous connections of entanglement, often lead us to ponder the very nature of reality. Yet it is crucial to remember that despite these philosophical depths, quantum mechanics is also an extraordinarily successful scientific theory, perhaps the most precisely tested and validated theory in all of physics. It is the bedrock upon which our understanding of chemistry, material science, and modern technology is built. Two of its most triumphant formulations are quantum electrodynamics, or QED, and quantum chromodynamics, or QCD. These theories represent our deepest insights into how particles interact through two of the fundamental forces, electromagnetism and the strong nuclear force. Quantum electrodynamics, often called the jewel of physics, describes how light and matter interact. It is a quantum field theory that beautifully explains everything from how electrons orbit atomic nuclei to the intricate dance of photons being emitted and absorbed. In QED, forces are not transmitted directly, but rather mediated by the exchange of virtual particles. For instance, when two electrons repel each other, they are not simply pushing. They are exchanging virtual photons, like two skaters throwing a ball back and forth, causing them to move apart. These virtual photons exist for such an incredibly brief time that they cannot be directly observed, a consequence of Heisenberg's uncertainty principle applied to energy and time. Yet their effects are profoundly real and precisely calculable. The predictions of QED, such as the anomalous magnetic moment of the electron, match experimental observations to an astonishing 10 decimal places, making it one of the most accurate theories ever devised. This incredible precision underscores that even the most ethereal concepts of quantum mechanics are rooted in a reality that we can measure and understand, albeit one that operates beyond our classical imaginings. Moving deeper into the atomic nucleus, we encounter quantum chromodynamics, or QCD. This theory describes the strong nuclear force, which is responsible for binding quarks together to form protons and neutrons, and subsequently holding these protons and neutrons within atomic nuclei. Quarks, the fundamental constituents of protons and neutrons, possess a property called color charge, an analogy to electric charge, but with three types: red, green, and blue. Just as electric charges interact by exchanging photons, color-charged quarks interact by exchanging particles called gluons. Gluons, unlike photons, carry color charge themselves, which leads to a peculiar and powerful characteristic of the strong force. It actually gets stronger with distance. Imagine trying to pull two magnets apart, and the further you pull them, the stronger the force becomes, eventually making it impossible to separate them. This is why we never observe free quarks in isolation. They are always confined within composite particles like protons and neutrons, a phenomenon known as color confinement. QCD, with its elegant description of quarks and gluons, completes our understanding of the fundamental building blocks of ordinary matter and the forces that hold them together, a testament to the profound order within the seemingly chaotic quantum realm. These quantum theories also provide the definitive explanation for the very structure and stability of atoms, and by extension, the diversity of the chemical elements. In the classical view, electrons orbiting a nucleus should quickly spiral inward due to electromagnetic attraction, causing atoms to collapse. However, quantum mechanics reveals that electrons exist in discrete energy levels or orbitals around the nucleus. They can only occupy specific quantized energy states, much like steps on a ladder, rather than being able to exist at any arbitrary height. An electron can jump between these energy levels by absorbing or emitting a photon of a precise energy, but it cannot exist in between. This concept of quantized energy, first proposed by Niels Bohr and later refined by Erwin Schrödinger, elegantly explains why atoms are stable and why they emit and absorb light at specific wavelengths, giving each element its unique spectral fingerprint. The Pauli exclusion principle, which we touched upon earlier, further dictates that no two electrons in an atom can occupy the exact same quantum state, preventing all electrons from piling into the lowest energy level. This principle is fundamental to the formation of the periodic table, determining how electrons fill successive shells and, in turn, dictating the chemical properties of elements. It is the quantum rules that ultimately orchestrate the intricate dance of electrons, shaping the very architecture of matter and enabling the rich tapestry of chemistry that forms our world. Ultimately, the quantum world teaches us that reality is fundamentally probabilistic. While classical physics offered a deterministic view where every event is predetermined by prior conditions, quantum mechanics introduces an irreducible element of chance. We can calculate the probabilities of various outcomes for a quantum event, but we cannot predict with certainty which outcome will actually occur until a measurement is made. This probabilistic nature is not a reflection of our ignorance, but rather a deep, inherent feature of the universe at its most fundamental scale. It means that the future, in a very real sense, holds genuine openness, a myriad of possibilities waiting to coalesce into a definite reality. This can be a profound and liberating thought, reminding us that even in the grand cosmic scheme, there is room for novelty and emergent possibilities. As we drift into the quietness of the night, perhaps we can embrace this quantum truth, that our own lives too are an unfolding of probabilities, a unique and beautiful journey through a universe that is both governed by fundamental laws and imbued with an astonishing inherent freedom. Let this gentle understanding of the micro-world carry you deeper into a peaceful state of rest, knowing that the smallest scales of existence hold the grandest implications for everything we perceive. Our exploration of quantum mechanics has illuminated a universe far stranger and more intricate than our classical senses could ever suggest, a world of intertwined possibilities and fundamental uncertainties. We have seen how the Standard Model brilliantly describes the electromagnetic and strong nuclear forces, and how the Higgs field bestows mass upon particles. Yet, there remains a monumental, unfinished symphony in our understanding, the reconciliation of quantum mechanics with the force of gravity. While quantum theories excel at describing the very small, Albert Einstein's theory of general relativity reigns supreme in describing gravity and the large-scale structure of the cosmos, from planets to galaxies. These two pillars of modern physics, incredibly successful within their own domains, speak different mathematical languages and offer fundamentally different pictures of reality, especially when we consider extreme conditions such as the heart of a black hole or the very first moments of the Big Bang. The challenge lies in their core assumptions. General relativity views space-time as a smooth, flexible fabric that can be warped by mass and energy, creating gravity. Quantum mechanics, on the other hand, suggests that all forces, including gravity, should be mediated by discrete particles, gravitons in this case, and that space-time itself should be quantized, existing in tiny indivisible packets, or quanta. This fundamental incompatibility leads to problems when physicists try to combine them. When the smooth, continuous geometry of space-time from general relativity is subjected to the probabilistic, fluctuating nature of quantum fields, the equations break down, yielding nonsensical infinities. It is as if we are trying to describe the ripples on a pond, quantum mechanics, with a theory designed only for the overall shape of the lake, general relativity, or vice versa. The scales at which these theories become relevant are vastly different, yet at the universe's most extreme points, they must converge. This quest for a theory of quantum gravity is perhaps the greatest challenge facing theoretical physics today, a silent call to uncover an even deeper, more unified truth about the universe. In response to this profound challenge, physicists have developed several theoretical frameworks, each attempting to bridge this divide, to weave gravity into the quantum tapestry. Two of the most prominent approaches are string theory and loop quantum gravity. String theory, a particularly elegant and ambitious framework, proposes that the fundamental constituents of the universe are not point-like particles, but rather tiny, one-dimensional vibrating strings, unimaginably small. Different vibrational patterns of these strings correspond to different particles, including the elusive graviton. This theory requires the existence of extra spatial dimensions beyond the three we perceive, curled up so tightly that they are currently undetectable. Loop quantum gravity, on the other hand, takes a different path, attempting to quantize space-time itself. It suggests that space-time is not a smooth continuum, but is instead composed of discrete, quantifiable loops, forming a fabric that is granular at the Planck scale, an incredibly tiny scale where our familiar notions of space and time are thought to break down. These theories, while still speculative and awaiting experimental verification, offer breathtaking visions of reality, hinting that the smooth, continuous universe we inhabit might be an illusion, an emergent property of a much more fundamental, discrete quantum structure. The implications of these ideas are truly profound, suggesting that space-time itself might not be a fundamental entity, but rather an emergent phenomenon. Just as the seemingly solid objects of our everyday world emerge from the probabilistic dance of quantum particles, so too might the smooth expanse of space and the relentless flow of time arise from a deeper, granular quantum substratum. Imagine looking at a photograph. From a distance, it appears as a continuous image, but zoom in close enough, and you reveal the discrete pixels that compose it. In a similar vein, the universe, at the most fundamental level, might be a network of quantum pixels of space-time, each carrying information about its geometry and connections. Our everyday experience of space as continuous and time as flowing smoothly would then be an approximation, valid at large scales, but breaking down at the smallest, most fundamental quantum limits. This perspective offers a serene, yet radical understanding that the very stage upon which the cosmic drama unfolds might itself be a participant in the quantum dance, constantly fluctuating and rearranging at scales far beyond our direct perception. This concept of emergent space-time also brings us to the Planck scale, a set of fundamental units derived from universal physical constants. the speed of light, Planck's constant, and the gravitational constant. At the Planck length, which is an unimaginably tiny 1.6 times 10 to the power of minus 35 meters, and the Planck time, an equally minuscule 5.4 times 10 to the power of minus 44 seconds, our current laws of physics begin to lose their meaning. This is where the quantum nature of gravity is expected to become dominant, where space-time itself is thought to become foamy and discontinuous. Below these scales, the very notions of where and when, as we understand them, may cease to apply. It is a boundary of human comprehension, a frontier where our current scientific tools and theories reach their limits. This ultimate fuzziness at the deepest level of reality can be a source of quiet contemplation, reminding us that the universe holds mysteries that transcend our immediate grasp, and that true understanding often lies beyond the veil of our everyday experience. Reflecting on these grand cosmic puzzles, on the quest to unify the very small with the very large, we can find a profound sense of our own place within this magnificent and mysterious unfolding. The knowledge that the space-time we navigate daily, the gravity that holds us to the Earth, might ultimately be an emergent property of a deeper quantum reality, invites us to view our existence with renewed awe. We are living, breathing configurations of quantum fields, experiencing an emergent classical reality, all while being part of a universe that is still revealing its most fundamental secrets. This ongoing journey of discovery, this gentle push against the boundaries of the known, is a testament to the enduring human spirit of inquiry. May these thoughts about the profound and elegant mysteries of the quantum world and our ceaseless quest to understand them bring a quiet sense of wonder and deepen your path towards a tranquil, restful sleep. The journey through the quantum realm has illuminated a universe of profound strangeness, where particles exist in states of superposition and are linked by entanglement, defying our classical intuitions. We've seen the intricate workings of quantum fields, giving rise to matter and forces, and the monumental quest to unify these microscopic laws with the cosmic grandeur of gravity. This ongoing search, particularly at the unimaginably tiny Planck scale, forces us to confront not just the limits of our theories, but perhaps the very nature of reality itself. If space-time is emergent, if particles are but ripples in fields, what then is the ultimate fabric of existence? This question leads us to ponder the role of information in the quantum universe, a concept that deepens the mystery and invites a quiet contemplation of what it means for anything to truly be. In the quantum world, information is not merely a collection of facts. It is a fundamental property, a conserved quantity. Unlike in classical physics, where information can be easily lost or destroyed, quantum mechanics suggests that information is never truly annihilated, only scrambled or transformed. This principle is famously highlighted by the black hole information paradox, a perplexing puzzle that arises when trying to reconcile quantum mechanics with general relativity. When matter falls into a black hole, it seems to vanish, taking all its quantum information with it. However, if information cannot be destroyed, then it must somehow be preserved, perhaps encoded on the event horizon, the black hole's boundary, or radiated away in a subtle form. While the exact resolution to this paradox remains a subject of intense research and debate, it underscores the profound importance of information in the quantum universe. It suggests that even the most extreme cosmic phenomena must adhere to the conservation of quantum information, implying a deeper, more resilient underlying order than we might initially perceive. This idea that information in its essence is eternal can bring a quiet sense of reassurance, like an echo of permanence within the ceaseless flow of change. It reshapes our understanding of what constitutes a fundamental building block of reality, moving beyond mere particles and forces to a realm where information itself plays a pivotal role, perhaps even as the ultimate substrate of all that exists. This brings us back to the enigmatic role of observation and the measurement problem, a concept that continues to challenge our intuitive grasp of reality. As we explored, a quantum system exists in a superposition of all possible states until it is measured, at which point it collapses into a single, definite outcome. This implies that the act of interacting with a system fundamentally influences its reality. It's not that we are simply passively observing an already fixed universe. Rather, our interactions, even at an unconscious level, play a role in defining the reality that emerges. This is a subtle yet profound distinction. The universe, at its deepest quantum level, is not a predetermined tapestry, but a canvas of potential, where the strokes are made through interaction. This shift from a purely objective, independent reality to one that is, in some sense, participatory, is one of the most radical departures from classical thought. It suggests a delicate interplay between observer and observed, a quiet dance of definition where possibilities condense into concrete events. To truly grasp this, one must let go of the ingrained notion of a fully formed, independent reality awaiting our discovery, and instead embrace a more fluid, interactive picture of existence. It is a profound invitation to consider our own role, however small, in the continuous unfolding of the cosmos. The ongoing scientific discourse surrounding the interpretations of quantum mechanics further highlights this deep philosophical challenge. The Copenhagen interpretation, perhaps the most widely accepted, emphasizes the probabilistic nature of quantum reality and the role of measurement in collapsing the wave function, without delving into what happens to the other possibilities. It suggests that asking what a particle is doing when not observed is simply not a meaningful question. Posits branch outcome. In this view, all possibilities are realized, but in separate, inaccessible universes. Then there are other interpretations, like pilot wave theory, which suggests that particles always have definite positions but are guided by an invisible quantum wave, or objective collapse theories, which propose that wave functions collapse spontaneously without the need for an observer when a certain physical threshold is met. The very existence of these diverse yet equally valid interpretations reminds us that even at the forefront of scientific discovery, there is ample room for profound philosophical contemplation. It is a gentle invitation to explore the boundaries of what we consider knowable, fostering a sense of humble wonder at the universe's capacity for mystery, and encouraging a peaceful acceptance of the multifaceted nature of truth. These deeply strange quantum phenomena, while seemingly confined to the subatomic world, ultimately underpin the stability and existence of everything we experience. The very fact that atoms hold together, that chemical reactions occur, that light interacts with matter in predictable ways, all depend on these quantum rules. Our bodies, the air we breathe, the ground beneath our feet, are all intricate arrangements of quantum particles behaving according to these probabilistic laws. The delicate balance between the inherent uncertainty of the quantum realm and the emergent stability of the macroscopic world is what allows for complexity, for life, and for consciousness to arise. It is a testament to the universe's exquisite design that such a fluid and probabilistic foundation can give rise to the structured and seemingly solid reality we inhabit. This grand coherence, emerging from such fundamental strangeness, can inspire a deep sense of peace, a quiet appreciation for the hidden mechanisms that allow us to simply be. It suggests that even our most profound experiences, our thoughts, and our very awareness are intricate patterns woven from the quantum fabric, an astonishing dance of energy and information that continually shapes our perceived reality. And so, as we reflect on these profound quantum insights, we are reminded that our understanding of the universe is an ever-evolving journey, a continuous unfolding of deeper truths. The micro-world, far from being a simple miniature version of our everyday experience, reveals a reality that is fundamentally different, more dynamic, and more mysterious. It teaches us about the interconnectedness of all things, the inherent role of observation, and the probabilistic nature of existence itself. This knowledge, rather than being unsettling, can bring a quiet sense of expansion, an awareness that we are part of a cosmic dance far grander and more intricate than we often realize. In this deep contemplation, we can find a gentle release, allowing our minds to settle into a state of tranquil wonder, knowing that the universe in all its quantum glory holds us gently within its vast and truly profound sleep. This intricate dance has led us to ponder the very nature of information and the emergent quality of space-time itself, particularly at the unimaginably tiny Planck scale. Yet, even as we consider these grand, abstract concepts, it is important to remember that the quantum world is not just about distant black holes or theoretical strings. Its strange rules govern the very fabric of our immediate reality, influencing even the most seemingly mundane aspects of our existence, including the solidity of the ground beneath our feet and the touch of our own hands. One of the most surprising revelations from quantum mechanics is the profound emptiness within what we perceive as solid matter. Our everyday intuition tells us that a table, a book, or even our own bodies are dense, tangible things, full of stuff. But when we delve down to the atomic scale, this intuition completely breaks down. An atom, the fundamental building block of all matter, is actually almost entirely empty space. Its tiny, incredibly dense nucleus composed of protons and neutrons is surrounded by a cloud of electrons. The scale of this emptiness is truly staggering. If an atom's nucleus were the size of a small pea placed at the center of a football stadium, the electron cloud would extend to the stadium's outermost walls. And everything in between would be nothing but vacuum. The electrons themselves are not tiny planets orbiting the nucleus. They exist as diffuse probability clouds, smeared out across this vast emptiness. So, when you hold an object in your hand, what you are fundamentally holding is mostly space, structured and held together by invisible forces and the peculiar rules of the quantum realm. This realization can be deeply calming, offering a new perspective on the illusion of solidity and the ephemeral nature of all physical forms. What then gives matter its apparent solidity? Why don't our hands pass right through a table, or why don't we fall through the floor? The answer lies in the electromagnetic force and a crucial quantum principle, the Pauli exclusion principle. At the atomic level, the outer layers of atoms are populated by electrons, which carry a negative electric charge. When two atoms come close to each other, their electron clouds strongly repel each other due to this like charge repulsion. This electromagnetic pushback is what we consciously perceive as the sensation of touch or solidity. There is no true contact in the classical sense, no merging of matter. Rather, it is a dance of repulsion, an invisible cushion of electric fields keeping atoms from overlapping. Furthermore, the Pauli exclusion principle, formulated by Wolfgang Pauli, states that no two identical quantum particles, particularly fermions like electrons, can occupy the exact same quantum state at the same time. This fundamental rule is not just a statistical oddity. It is a profound law built into the very fabric of the universe that dictates matter's structure. It is what prevents all electrons from collapsing into the lowest energy level around an atom, ensuring that atoms maintain their distinct shells and that different elements exhibit unique chemical properties. Without this principle, all matter would simply collapse into an undifferentiated, dense blob, and the complexity of the universe, including life itself, would be impossible. So, the solidity we feel is a direct consequence of these quantum rules, a testament to the elegant order emerging from the chaotic quantum dance. The very emptiness of space, even the vacuum between stars and galaxies, is also far from truly empty, as we've noted. It is a vibrant, restless sea of quantum fields, constantly giving rise to virtual particles that flicker into existence and vanish. This zero-point energy, or vacuum energy, suggests that the lowest possible energy state of space is not zero, but rather a teeming, dynamic realm of potential. This continuous effervescence of the quantum vacuum has profound implications, extending to the accelerating expansion of the universe itself, driven by what we call dark energy. While the precise connection between vacuum energy and dark energy is still one of the greatest unsolved puzzles in physics, the underlying idea is that the very void of space possesses an intrinsic energy that can exert a repulsive force, gently stretching the cosmos apart. This means that even the most seemingly empty regions of the universe are alive with activity, a constant, subtle hum of creation and annihilation that shapes the grand cosmic ballet. It is a quiet, powerful reminder that the universe is always in motion, always evolving, even in its deepest, most tranquil expanses. The intricate interplay of these quantum phenomena, wave-particle duality, superposition, entanglement, decoherence, the vacuum energy, and the fundamental forces, ultimately gives rise to the complex, diverse, and dynamic universe we inhabit. From the fusion reactions that power stars enabled by quantum tunneling to the intricate chemical bonds that form molecules and ultimately life, the quantum rules are the unseen architects of reality. Every atom in your body, every thought in your mind, every sensory experience is a manifestation of these deep, probabilistic processes. This profound interconnectedness, where the smallest ripples in quantum fields give rise to the grand structures of the cosmos, can evoke a deep sense of belonging. We are not mere spectators in this quantum universe. We are integral participants, woven from its very fabric, continuously engaged in its intricate dance. As we gently conclude our reflections on how the micro-world works, let us carry this sense of wonder and interconnectedness into the quietude of the night. The universe, at its smallest scales, is a place of ceaseless activity, profound mystery, and elegant laws, a realm where intuition gives way to the astonishing beauty of quantum reality. May the understanding of this intricate, probabilistic dance, from the emptiness within atoms to the vibrant energy of the vacuum, bring a deep and tranquil peace to your mind. Fall asleep with the awareness that you are a complex, miraculous expression of these fundamental cosmic principles, a brief but brilliant pattern in the infinite tapestry of existence. Good night. As we consider the intricate patterns woven from the quantum fabric that compose our very being, a fascinating and highly speculative frontier of physics emerges, the realm of quantum biology. This nascent field explores whether quantum phenomena, typically thought to occur only in isolated, extremely cold or very small systems, might actually play a crucial role in the warm, noisy, and complex environment of living organisms. It challenges the long-held assumption that biological systems are too large and too messy for delicate quantum effects, like superposition and entanglement, to persist. Yet, evidence is slowly mounting that nature might have found ingenious ways to harness these quantum quirks for essential biological processes. Imagine for a moment the subtle whispers of quantum mechanics guiding the fundamental operations of life itself, a profound and elegant possibility that could redefine our understanding of biology. One of the most compelling examples comes from photosynthesis, the process by which plants convert sunlight into energy. Early stages of photosynthesis involve light-harvesting proteins that capture photons and efficiently transfer their energy to reaction centers. Research suggests that this energy transfer might be guided by quantum coherence, a state similar to superposition where energy can explore multiple pathways simultaneously, essentially finding the most efficient route through a complex molecular network. This quantum shortcut allows plants to achieve near-perfect efficiency, a feat that would be impossible if energy transfer relied solely on classical random diffusion. Another intriguing area is the navigation of migratory birds. Some theories propose that birds use Earth's magnetic field to orient themselves, and that this magnetic sense could involve quantum entanglement within specific molecules in their eyes. The entangled electrons in these molecules might react differently to subtle variations in the magnetic field, providing the birds with a quantum compass. These are not definitive proofs, but compelling hints that life, at its most fundamental level, might be leveraging the strange rules of the quantum world to its advantage, quietly operating at the very edge of what we understand about physics and biology. The potential for quantum effects to influence even higher-level biological functions, such as consciousness itself, remains a deeply controversial and highly speculative area. Some pioneering thinkers, like Roger Penrose and Stuart Hameroff, have proposed that consciousness might not be a purely classical emergent property of complex neural networks, but rather could involve quantum processes occurring within the microtubules of brain neurons. This orchestrated objective reduction theory suggests that consciousness arises from quantum coherence and its subsequent collapse, linking the subjective experience of awareness directly to the fundamental uncertainty of the quantum realm. While this idea is far from mainstream acceptance and faces significant scientific hurdles, it represents a bold attempt to bridge the explanatory gap between the physical brain and the phenomenon of consciousness, offering a vision where our very thoughts and perceptions are intricately woven into the quantum tapestry. It asks us to consider whether the subjective inner world we inhabit might be a direct reflection of the universe's most profound and subtle mechanics, inviting a deep personal contemplation of our own existence as a quantum phenomenon. The very act of observing, of forming a thought, might be a tiny echo of the universe's own quantum choices, a continuous process of reality solidifying from a sea of possibilities. Beyond biology, the practical applications of quantum mechanics continue to expand, reshaping our technological landscape in ways that were once considered science fiction. We've already mentioned quantum computing, but consider the everyday technologies that rely on these principles. Lasers, which power everything from fiber optic communication to medical surgery, operate by precisely controlling the quantum transitions of electrons within atoms. Semiconductor devices, the very heart of all modern electronics, from your smartphone to supercomputers, function because of our ability to manipulate the quantum behavior of electrons in materials. Magnetic resonance imaging, or MRI, a vital diagnostic tool in medicine, harnesses the quantum property of nuclear spin to create detailed images of the human body. These technologies, now commonplace, are powerful testaments to the predictive power and tangible reality of quantum mechanics. They demonstrate that even if the quantum world feels abstract or counterintuitive, its rules are rigorously applied and thoroughly understood enough to build the foundations of our modern world. It is a quiet miracle of engineering, transforming the elusive principles of the very small into tools that profoundly shape our daily lives, a harmonious blend of abstract theory and concrete utility. Yet, despite these incredible successes, the philosophical implications of quantum mechanics continue to provoke deep thought. The measurement problem, the question of when and how a quantum superposition collapses into a definite state, remains an area of active debate and interpretation. Some physicists lean towards the idea that the universe simply chooses an outcome when a measurement occurs, while others, following the many worlds interpretation, believe that all possible outcomes are realized in branching parallel universes. These interpretations are not mere academic curiosities. They challenge our most fundamental assumptions about the nature of reality, causality, and even the role of consciousness in the cosmos. There is no single, universally accepted answer, and perhaps there never will be one that fully satisfies our classical intuition. This ongoing mystery, this graceful ambiguity at the heart of existence, can be a source of profound peace rather than anxiety. It invites us to embrace the unknown, to find beauty in the questions that remain unanswered, and to accept that the universe is far richer in its possibilities than any single fixed reality could ever be. This grand tapestry of quantum phenomena, from the vibrating strings of theoretical physics to the quantum whispers within living cells, constantly reshapes our understanding of ourselves and our place in the cosmos. We are, quite literally, made of probabilities, existing in a reality that is both profoundly structured and inherently fluid. The gentle hum of virtual particles in the vacuum, The entangled dance of distant photons and the subtle quantum coherence within our own biological processes are all part of the same magnificent, interconnected story. Embracing this perspective can bring a deep sense of calm, dissolving the rigid boundaries between self and universe, between observer and observed. It encourages us to see ourselves not as separate entities, but as an integral, active part of the universe's self-organizing quantum dance. The very act of perceiving, of contemplating these ideas, is a quantum process in itself, a moment where the vastness of the cosmos is reflected in the intricate workings of our own minds. This realization that our internal world mirrors the external quantum reality can be a source of profound serenity, a profound awareness of the seamless unity between the microcosm and the macrocosm. It is a reminder that even in the quietest moments, the universe is alive within us. May these deep thoughts about the intricate and wondrous world of quantum mechanics carry you into a realm of tranquil sleep. Remember that the universe, at its most fundamental level, is a place of profound mystery and elegant laws, a continuous dance of possibilities from which all reality, including your own, emerges. You are, in every atom and every interaction, a part of this astonishing quantum tapestry. Fall asleep with this feeling of serene wonder and an expanded understanding of the cosmos that cradles us all. Good night.